Hi there, and welcome to Tech with Shaping Pixel. We are bringing free certification course. In this video, we are diving into the AWS Certified Advanced Networking Specialty, ANS-C01 full crash course. We have also included the latest real exam questions and answers for the AWS Certified Advanced Networking Specialty exam. If you haven't subscribed to our YouTube channel yet, we'd love for you to join our growing community. Just hit that subscribe button. Want a downloadable PDF of these questions and answers? You can grab it from our website, www.shapingpixel.com. Full link is in the description below. Let's get started and jump right into the questions. This certification is designed for professionals with experience in designing, implementing, and operating complex networking architectures on Amazon Web Services, or AWS, and hybrid environments. AWS recommends at least 5 years of general networking experience and 2 years in cloud or hybrid networking. The exam is divided into 4 domains: network design, network implementation, network management and operation, and network security, compliance, and governance. Each domain covers specific skills, from designing global architectures to securing network traffic and ensuring compliance. Network design focuses on optimizing user performance, designing DNS solutions, integrating load balancing, and creating routing strategies across multiple AWS accounts and regions. Network implementation tests your ability to connect on-premises networks to AWS using site-to-site VPNs and Direct Connect, and to automate network infrastructure. Network management and operation covers maintaining connectivity, monitoring traffic, and optimizing for performance and cost. Network security, compliance, and governance assesses your ability to secure networks using AWS WAF, Shield, firewalls, and encryption, as well as monitoring and auditing network activity. Apart from this crash course, cover the preparation question and answers from our YouTube channel at Tech with Shaping Pixel. Review the official AWS exam guide, understand each domain's requirements, and practice with AWS networking tools like CloudWatch, VPC Flow Logs, and Route 53. Good luck on your certification journey. AWS Networking and Virtual Private Cloud (VPC). Let's break down what a virtual private cloud, or VPC, really is. In the world of AWS, or Amazon Web Services, a VPC is your own private section within the AWS cloud. Think of it as your personal, secure space in a massive digital environment. When you create a VPC, only your AWS account can access it by default. It is completely isolated from the millions of other VPCs created by customers around the globe. No one else can access your VPC, and you cannot access theirs, ensuring strong security and privacy. So, what can you do with a VPC? It allows you to deploy resources like compute power, storage, databases, and networking tools. This means you can build and launch your own solutions within the cloud, all inside your protected environment. Creating a VPC is straightforward. You simply give it a name and define an IP address range using something called a classless interdomain routing block, or CIDR block. By default, you can have up to 5 VPCs per region in your AWS account. Security is essential in Amazon Web Services, or AWS, especially when managing your virtual private cloud. 2 key components for controlling traffic are Network Access Control Lists, or NACLs, and security groups. NACLs, or Network Access Control Lists, act as virtual firewalls at the subnet level. They control both incoming and outgoing traffic for each subnet in your virtual private cloud. By default, a new subnet in AWS is associated with the NACL that allows all traffic, but this is not secure. It is best practice to configure NACLs to only permit the traffic you want. For example, in a public subnet hosting web servers, you might allow inbound HTTP on port 80 and HTTPS on port 443 from any source. All other inbound traffic would be denied by a default rule. Outbound rules can be set to allow all traffic to any destination, but you can restrict these as needed. Remember, NACLs are stateless. This means return traffic must be explicitly allowed in both inbound and outbound rules. Security groups, on the other hand, control traffic at the instance level, providing another layer of protection for your AWS resources. Let us break down the difference between security groups and network access control lists, or NACLs, in cloud security. Both filter traffic, but they operate at different layers and serve unique purposes. NACLs, or Network Access Control Lists, work at the subnet level. Imagine 3 private subnets, each with its own IP address range. A single NACL can be associated with all 3, controlling which types of traffic are allowed in or out of the subnet. Security groups, on the other hand, operate at the instance level. For example, you might have a security group attached to your database instances. These groups specify which sources can access specific ports, like allowing only MySQL traffic from a certain subnet. When a request is made, it first passes through the NACL at the subnet boundary. If allowed, it then reaches the security group at the instance. If the security group has a rule for that source and port, access is granted. Otherwise, the traffic is dropped. NACLs are stateless, requiring rules for both inbound and outbound traffic. Security groups are stateful, so return traffic is automatically allowed. Together, they provide layered security for your cloud resources. Let us break down the role of a NAT gateway in a virtual private cloud, or VPC. Imagine a VPC with 2 subnets, one public, one private. The private subnet is where your application servers, like EC2 instances, live. But these servers need updates from the internet. Here is the challenge. Private subnets cannot access the internet directly. That is where a NAT gateway comes in. Placed in the public subnet, the NAT gateway gets a public elastic IP address. When your private EC2 instances need to download updates, their traffic is routed to the NAT gateway. The NAT gateway then forwards the request to the internet and brings the data back, keeping your private subnet isolated from direct internet exposure. A key security feature: the NAT gateway only allows outbound connections from within your VPC. It blocks any inbound traffic initiated from the internet. Plus, AWS manages the NAT gateway for you, making setup simple. For high availability, you need a NAT gateway in each public subnet across different availability zones. In short, a NAT gateway lets private subnets securely access the internet for updates while blocking unsolicited inbound traffic, helping you keep your EC2 instances patched and secure. Let us explore how to securely access private Amazon EC2 instances in Amazon Web Services, or AWS, using a bastion host. Imagine you have EC2 instances in a private subnet, but you need remote access for maintenance or updates. A bastion host is an EC2 instance placed in a public subnet within your virtual private cloud, or VPC.
This host acts as a secure gateway, allowing engineers to connect from the internet to the private subnet. The public subnet connects to the internet via an internet gateway, while the private subnet remains isolated for security. To keep your Bastion host secure, it must be hardened and tightly controlled. Assign a security group that only allows secure shell or SSH access on port 22 from specific IP addresses, such as your engineer's home office. The private EC2 instances have their own security group, permitting SSH only from the Bastion host's security group. Engineers connect to the Bastion host using SSH and a private key. For best security, use SSH agent forwarding so private keys for the private instances stay on your local machine, never on the Bastion host. This keeps your environment secure. A virtual private network, or VPN, is a secure way to connect two remote networks over the internet. In Amazon Web Services, or AWS, VPNs help link your on-premises data center to your virtual private cloud, or VPC. Imagine your VPC in AWS and your data center in another location. With a VPN, you can securely connect resources in your private subnet, like EC2 instances, to your on-premises network, even if your subnet has no direct internet access. On the AWS side, you attach a virtual private gateway to your VPC. In your data center, you set up a customer gateway, which can be hardware or software. The VPN tunnel is initiated from the customer gateway. Update your route tables so AWS resources know how to reach your data center. Security groups must also allow the right protocols, like SSH or RDP, from your data center's IP range. Direct Connect is another way to link your data center to AWS, but it does not use the public internet. Instead, it uses dedicated private infrastructure. Your data center connects to a Direct Connect location, which bridges your network to AWS. This setup allows access to both private VPC resources and public AWS services. VPC peering is a way to connect two virtual private clouds, or VPCs, so their resources can communicate securely. Unlike VPN connectivity or Direct Connect, which link your on-premises network to a VPC, VPC peering connects VPCs directly. Each VPC might contain resources like EC2 instances or databases. With VPC peering, these resources can talk to each other, even if the VPCs are in different regions. The connection itself is managed by Amazon Web Services, or AWS, making it highly resilient with no single point of failure or bandwidth bottlenecks. VPC peering is always a one-to-one connection. If you have 3 VPCs, each pair needs its own peering connection. Also, the IP address ranges, known as CIDR blocks, of the VPCs cannot overlap. If 2 VPCs share the same address range, peering is not possible. To set up peering, the owner of one VPC sends a request to another. Once accepted, both VPCs update their route tables to allow traffic. Security groups must also be updated to permit communication. VPC peering is a simple, robust way to connect VPCs for secure resource sharing. Just remember the one-to-one rule and avoid overlapping IP addresses. Let's break down AWS Transit Gateway, a powerful tool for simplifying network connectivity in Amazon Web Services, or AWS. As organizations grow, managing connections between multiple virtual private clouds, or VPCs, and remote locations becomes increasingly complex. Traditionally, VPC peering connects VPCs directly, but each connection is one-to-one. Imagine having 4 VPCs and 2 remote offices. To connect everything, you would need multiple VPC peering and VPN connections. quickly leading to a tangled web that is difficult to manage and scale. AWS Transit Gateway changes the game by acting as a central hub. Instead of creating individual connections between every VPC and remote location, each simply connects once to the Transit Gateway. Whether using VPN, Direct Connect, or VPC connections, all traffic routes through this single hub. Adding new VPCs or locations? Just connect them to the Transit Gateway and they can communicate with the entire network instantly. This approach streamlines network management, centralizes routing, and makes monitoring much easier. All network traffic and connectivity can be viewed and managed from one dashboard, saving time and reducing complexity. AWS Transit Gateway, the smarter, simpler way to connect your AWS infrastructure. Subnetting is the process of dividing a larger network, known as a CIDR block, into smaller, more manageable networks using different subnet masks. This allows you to segment your network and make better use of your available IP address space. For example, if you have a CIDR block of 10.0.0.0/16, you can split it into two subnets using a /17 mask. This creates two separate networks, 10.0.0.0/17 and 10.0.0.128.0/17. When creating an Amazon Web Services Virtual Private Cloud, or AWS VPC, you must specify a CIDR block. This defines the entire IP address space for your VPC. You can then create multiple subnets within this range, ensuring you have enough IP addresses for your resources. AWS reserves the first 3 host IP addresses in each subnet for internal use: the VPC router, AWS DNS, and future services. For example, in a subnet, addresses like 10.0.32.1 and .2 are reserved. If you need IPv6, AWS assigns a /56 IPv6 CIDR block from their pool rather than letting you choose your own range. Use online subnet calculators to help plan your network and ensure you allocate enough addresses for your needs. Why should we subnet our virtual private clouds, or VPCs? Subnetting is more than just a technical requirement. It is a strategic approach to organizing and securing your cloud infrastructure. By creating multiple subnets, you can logically divide your network. For example, you might have one subnet for databases, another for application servers, and a third for web infrastructure. This separation makes managing resources much easier and more efficient. Grouping similar resources in dedicated subnets enhances security. You can use Network Access Control Lists, or NACLs, to filter traffic at the subnet level. As one network engineer put it, does your house have more than one room? Each room serves a different purpose, just like subnets in your VPC, said a network engineer. Subnetting also lets you create both public and private subnets. Public subnets allow internet access, while private subnets are isolated from the internet, providing an extra layer of protection for sensitive resources. With multiple subnets, you can control routing for each group of resources and ensure high availability by deploying subnets across different availability zones. Subnetting your VPC brings structure, security, and flexibility to your cloud environment. Amazon Web Services Virtual Private Cloud, or AWS VPC, lets you create isolated networks in the cloud. Within a VPC, subnets divide your network into smaller segments, each with its own unique settings and controls. When you create a subnet in AWS, it comes with several important components. The summary section displays the subnet ID, a unique identifier, and its tag name. You will also see the IPv4 and IPv6 CIDR blocks, which define the subnet's address range. The VPC section shows which VPC the subnet belongs to, and the Available IPs field tells you how many addresses remain for your resources. Each subnet is tied to a single availability zone and cannot span multiple zones. Network Access Control Lists, or NACLs, are rule-based tools for controlling inbound and outbound traffic at the subnet level. NACLs are stateless, so you must specify rules for both directions. Rules are read in order, so careful numbering is important. By default, subnets use the VPC's default NACL, which allows all traffic. Subnets also include route tables, flow logs for monitoring traffic, and customizable tags for organization. The auto-assign public IP and IPv6 settings determine if new resources get public addresses automatically. Let us break down the key differences between public and private subnets in Amazon Web Services, or AWS. Understanding these differences is essential for designing secure and scalable cloud environments. A public subnet is defined by its ability to access the internet directly. To achieve this, you must first attach an internet gateway to your virtual private cloud, or VPC. The Internet Gateway is a managed AWS service that scales automatically and acts as your network's bridge to the outside world. Next, you need to update the subnet's route table by adding a default route with a destination of 0.0.0.0/0 and targeting the Internet Gateway. Your subnet becomes public. However, there is more to enabling internet access. Each instance in the public subnet must have a public Internet Protocol IP, or IP address. Additionally, the Network Access Control List, or NACL, must allow the necessary inbound and outbound traffic. Otherwise, connectivity issues may arise. By default, AWS does not automatically assign public Internet IP addresses to new instances. You can enable auto-assignment in the subnet settings or manually assign them as needed. Virtual Private Cloud Peering, or VPC peering, lets you connect two or more virtual private clouds together using either Internet Protocol version 4 or Internet Protocol version 6. This connection makes the VPCs act as if they are part of the same network. Once you establish a peering connection, resources in one VPC can access resources in the other. However, there are important design considerations. The most critical is your CIDR block ranges. CIDR stands for Classless Interdomain Routing, and it defines the range of IP addresses for your VPC. If your VPCs have overlapping or duplicate CIDR ranges, you cannot peer them together. Planning unique CIDR blocks for each VPC is essential if you want to set up multiple peered VPCs. It is also important to know that you cannot daisy-chain VPCs and expect them all to communicate across a single network. Each VPC will only communicate directly with its peer. For example, if VPC1 is peered with VPC2 and VPC2 is peered with VPC3, VPC1 and VPC3 cannot communicate unless you create a direct peering connection between them. Interestingly, if VPC1 and VPC3 have identical CIDR blocks but are only peered with VPC2,
this configuration is allowed. However, if you try to pair VPC1 and VPC3 directly, the connection will fail due to overlapping CIDR blocks. Routing in Amazon Web Services, or AWS, is all about directing network traffic to the right destination. Inside a virtual private cloud, or VPC, AWS manages virtual routers for you, so you never need to set up physical routers yourself. Each VPC comes with a main route table, which is automatically linked to your subnets unless you specify a custom route table. Every subnet must have one associated route table, but multiple subnets can share the same table. Remember, a subnet can only be associated with one route table at a time. The main route table cannot be deleted, but you can customize it by adding or removing routes. If you want to change routing without disruption, create a custom route table associated with the subnet, test it, and then set it as the new main route table. Route tables include a summary, routes, subnet associations, route propagation, and tags. Each table has a unique ID, and you can see which subnets are associated, explicitly or implicitly. Every route table includes a local route, allowing all subnets within your VPC to communicate. To reach external networks, you must add specific routes pointing to gateways, like a virtual private gateway for VPN connections.
Let us break down how AWS route tables decide where your network traffic goes, especially when routes overlap. Understanding these priorities is essential for troubleshooting and designing efficient cloud networks. Let us explore some example scenarios of virtual private cloud peering, or VPC peering solutions. Understanding these configurations is essential for enabling secure and efficient connectivity between your cloud networks. For two VPCs to communicate over a peering connection, abbreviated as PCX, their IP address ranges, or CIDR blocks, must not overlap. Each subnet that needs connectivity must have a static route in its route table, pointing to the peered VPC's CIDR block via the PCX. For example, if subnet A in VPC1 has a route to VPC2's CIDR block, and subnet C in VPC2 has a route to VPC1's CIDR block, these subnets can communicate. However, subnets without such routes remain isolated. When three VPCs are peered, each VPC must have separate peering connections and route tables configured for every other VPC. For instance, VPC3 uses a different PCX to reach VPC1 than VPC2 does. Careful configuration ensures correct traffic routing in complex topologies. If two VPCs have identical CIDR blocks, routing becomes tricky. Without unicast reverse path forwarding, responses may be misrouted. Using the longest prefix match in route tables helps direct traffic to the correct VPC even with overlapping address spaces. Virtual private gateway routing is a key part of connecting your Amazon Web Services, or AWS, virtual private cloud, or VPC, to your corporate network using a virtual private network, or VPN. Let us break down how this works. First, you need to create and attach a virtual gateway to your VPC. This virtual gateway acts as the bridge between your AWS environment and your external corporate network. While there are many steps involved in setting up a VPN, for routing purposes, attaching the virtual gateway is the essential first step. Once your virtual gateway is attached, you can update the route tables for any subnets that need to communicate with your corporate data center. For example, If your AWS subnet is 10.0.2.0/24, you might add static routes to two 172.16 subnets in your corporate network, with the virtual gateway as the target. Enabling route propagation on your virtual gateway automatically includes VPN routes in your route tables. If you do not enable propagation, you must manually add static routes for each network you want to reach through the VPN. One important note: AWS does not currently support IPv6 traffic across VPN connections using a virtual private gateway. Let's explore how to configure routing for both Internet gateways and NAT gateways in your Amazon Web Services Virtual Private Cloud, or VPC. Understanding these configurations is essential for managing public and private subnet connectivity. An Internet gateway, often called an IGW, is a highly available AWS managed service that enables communication between your VPC and the Internet. To make a subnet public, you attach an Internet gateway to your VPC and update the subnet's route table. Typically, you add a route with the destination of 0.0.0.0/0, which means all unknown traffic is sent to the Internet gateway. This catch-all route ensures your public subnet can reach the Internet. Routing for a network address translation, or NAT gateway, is a bit different. A NAT gateway allows instances and private subnets to access the Internet for tasks like operating system updates while blocking inbound Internet-initiated connections. The private subnet's route table points to the NAT gateway, which must reside in a public subnet. This setup keeps your private resources secure but connected. If you have multiple availability zones, deploy a NAT gateway in each one. Update private subnet route tables to point to their local NAT gateway. This ensures Internet access remains available even if one zone fails. Configuring routing for Internet and NAT gateways is key for secure, reliable VPC connectivity. Virtual Private Cloud Sharing, or VPC sharing, is a powerful feature in cloud computing that allows multiple teams to use shared networking resources while still maintaining security and efficiency across an organization's cloud environment. When every team manages their own VPCs, mistakes can happen. Overlapping IP ranges or misconfigured security settings can create vulnerabilities and connectivity issues. Centralizing VPC management ensures consistent security, compliance, and networking standards, freeing up application teams to focus on innovation. With VPC sharing, a dedicated AWS account, known as the VPC owner, creates and manages the VPC and its resources. Other AWS accounts, called VPC participants, are granted access to specific subnets within the shared VPC. This setup allows participants to deploy their own resources, like EC2 instances, while the owner maintains control over core networking components. VPC sharing reduces administrative overhead, prevents misconfigurations, and optimizes costs. Best practice is to use a dedicated networking AWS account for creating, securing, and sharing VPCs, ensuring a robust and scalable cloud foundation. Instead of 3 separate NAT gateways for 3 AWS accounts, VPC sharing enables all accounts to use a single NAT gateway, cutting costs and simplifying management. AWS Resource Access Manager, or RAM, is a powerful tool that helps you share centralized resources across your AWS environment. With RAM, you can share a wide range of AWS resources, including Aurora database clusters, dedicated hosts, resource groups, and virtual private cloud subnets. To get started with RAM, the first step is to enable sharing. You can do this easily through the Resource Access Manager console or by using the AWS Command Line Interface, or CLI. Once sharing is enabled, you can create a resource share. This involves naming your share and selecting the resources you want to share. For example, you might create a share called DevTeam1 and include 3 subnets from the same virtual private cloud.
After selecting your resources, you assign permissions to control what others can perform on the shared resources. If you are satisfied with the permissions, you move on to identify the principals or users you want to share with. Selecting an organizational unit or OU allows sharing with all AWS accounts in that group. Finally, you complete the wizard, and the shared resources, such as the 3 subnets, will quickly appear in the virtual private cloud console of the selected AWS accounts, making collaboration seamless and efficient. Virtual Private Cloud Sharing, or VPC sharing, in Amazon Web Services allows multiple AWS accounts within the same organization to use a single VPC. This setup helps teams collaborate efficiently, but there are important rules and limitations to keep in mind. The VPC owner can only share VPCs with accounts in their own organization, and default VPCs in each region cannot be shared. Participants in a shared VPC must use their own security groups and cannot use the default security group or those created by others. While participants can create application and network load balancers and register their own targets, only the VPC owner can deploy gateway load balancers. Each participant is responsible for the resources they deploy, such as EC2 instances, RDS databases, or Redshift clusters. Participants are billed for their own deployed resources and for data transfer, including interavailability zone transfers, VPC peering, and AWS Direct Connect gateways. The VPC owner may incur charges for NAT gateway processing, virtual private gateways, and VPC endpoints. If a subnet is unshared, participants cannot create new resources there, but existing resources continue running. Participants can still manage their resources, and the VPC owner cannot delete the subnet until all resources are removed. Today, let's spotlight a powerful tool in your Amazon Web Services toolbox, the VPC Reachability Analyzer. Whether you are new to Amazon Web Services or a seasoned pro, this feature can save you time and frustration. In the past, diagnosing connectivity issues in cloud networking meant checking endless settings like security groups, elastic IP addresses, and internet gateways. Missing just one step could leave you stuck, searching for answers and losing productivity. The VPC Reachability Analyzer changes that. The VPC Reachability Analyzer lets you test connectivity between 2 points in your architecture. It starts at your chosen source, checks each network component along the path, and generates a report highlighting any issues. You can analyze connections between instances, VPN gateways, network interfaces, internet gateways, VPC endpoints, and even across VPC peering connections. For example, if 2 instances cannot connect, the analyzer identifies exactly where the problem lies, such as missing inbound rules in a security group. Fix the rule, rerun the analysis, and instantly see if connectivity is restored. At just 10 cents per run, it is affordable and efficient. The VPC Reachability Analyzer makes troubleshooting cloud networking straightforward, helping you learn and build with confidence. Let's break down elastic IP addresses, or EIPs, and why they matter for your AWS infrastructure. When you launch an EC2 instance, you can get a public IP address, but it is not persistent if you stop or restart the instance. An elastic IP address is a persistent, public IPv4 address you can allocate to your AWS account. Unlike standard public IPs, which change when you stop or start your instance, an EIP stays the same. This is essential when you need a consistent public endpoint. You can associate an EIP with an EC2 instance or an Elastic Network Interface, or ENI. If you move the EIP between instances, the address remains unchanged. However, if you detach an EIP and do not associate it with a running instance, AWS will charge you for it. You cannot convert a regular public IP to an EIP.
If you assign an EIP to an instance with a public IP, the original address is released. Always release unused EIPs to avoid unnecessary charges. Elastic IP addresses provide reliable, persistent public connectivity for your AWS resources, making them ideal for applications that require stable endpoints. Elastic Network Interfaces, or ENIs, are virtual network cards you can create and manage within your Virtual Private Cloud, or VPC. ENIs let you add flexible networking options to your Amazon EC2 instances. Every EC2 instance starts with a primary network interface called ETH0, which cannot be removed. However, sometimes you need more than one network interface, such as when setting up a management network. In these cases, you can add a secondary ENI. To add a new ENI, go to the AWS Management Console, select Network Interfaces, and create one in your desired subnet. For example, you might create a management interface in a subnet like 10.0.3.0. Once created, attach it to your instance. Now your instance will have both ETH0 in the production subnet and ETH1 in the management subnet, allowing it to communicate across different networks. Detaching an ENI is simple. Select the interface and detach it. The ENI keeps its configuration, including its IP address, even after detachment. You can also delete the ENI if it is no longer needed. ENIs provide flexibility for your EC2 networking needs. Remember, the number of ENIs you can attach depends on your instance type. Use ENIs to connect instances to multiple subnets or networks as your architecture requires. If you want to boost your Amazon EC2 instance's network performance, enabling enhanced networking with the Elastic Network Adapter, or ENA, is the way to go. Let's explore how ENA can transform your cloud experience. The Elastic Network Adapter is a custom network interface designed to optimize network speeds for EC2 instances. With ENA, you can achieve network speeds of up to 100 gigabits per second on supported Linux compute instances. However, ENA is only available on certain EC2 instance types and requires Linux kernel versions 2.6.32 or 3.2 and above. Enhanced networking with ENA delivers higher bandwidth, increased packets per second performance, and lower latency. Best of all, these improvements come at no extra cost. If you launch an instance using Amazon Linux 2 or the latest Amazon Linux AMI on a supported instance type, enhanced networking is enabled by default. To enable enhanced networking, ensure the ENA module is installed and the ENA support attribute is set. This setup is essential for unlocking ENA's full potential. To confirm the ENA module is installed, run modinfo ENA in your terminal. To check the ENA support attribute, use the AWS command line interface with your instance ID. Let us break down VPC endpoints in Amazon Web Services, or AWS. VPC endpoints let you privately access AWS services using the AWS internal network, so you do not need an internet gateway, NAT gateway, virtual private network, or direct connect connection. This keeps your data secure and off the public internet. There are two types of VPC endpoints. First, interface endpoints. These are elastic network interfaces, or ENIs, placed within your subnet. They use AWS Private Link to create private, secure connections between your VPC, AWS services, and even on-premises applications. One important detail: communication must start from your VPC. The associated service cannot initiate a connection to your VPC. The second type is gateway endpoints. These are used in your route tables to connect to specific AWS services. Currently, only Amazon Simple Storage Service, or S3, and DynamoDB are supported. When you create a gateway endpoint, you select which route tables to update, and AWS automatically adds the necessary routes. Note that gateway endpoints only work with IPv4. When you create an interface endpoint, AWS sets up a private DNS hostname. Your applications keep using the default service name, but now request route privately within AWS. No reconfiguration needed. AWS Global Accelerator is a global service designed to speed up and secure your user traffic. Instead of relying on the unpredictable public internet, it uses the AWS global infrastructure to route both UDP and TCP traffic to your applications more reliably and efficiently. With AWS Global Accelerator, you get 2 static Internet Protocol version 4 addresses linked to a domain name system name. These addresses serve as fixed entry points to your application, whether it is behind a load balancer, an Amazon Elastic Compute Cloud instance, or an Elastic IP address. You can map these addresses to multiple endpoints across different regions, boosting performance and availability. Global Accelerator intelligently routes requests using AWS's worldwide edge locations, always choosing the lowest latency path and avoiding unhealthy resources. This ensures high availability and seamless regional failover. You can control traffic distribution with traffic dials and assign weights to endpoints, making blue-green deployments and gradual rollouts straightforward. To set up, create your accelerator. Choose your Internet Protocol version 4 addresses. Add listeners for your desired protocols and ports. Configure endpoint groups by region, and register your endpoints. Health checks keep your application reliable, and changes can be made without updating your static addresses or domain name system name.
Let us explore AWS Private Link, a service designed to simplify secure connectivity between different organizations on Amazon Web Services, or AWS. Imagine needing to access data in another company's virtual private cloud, or VPC, but only through private IP addresses. AWS Private Link connects 2 main parties: service providers who offer a service and service consumers who use it. With Private Link, service providers can create endpoint services that consumers access privately and securely, all within the AWS global network. This means there is no need to expose services to the public internet. There are 3 main reasons organizations use AWS Private Link. First, many AWS partners like Datadog, MongoDB, NetApp, Snowflake, and Salesforce offer their services through Private Link, allowing customers to connect without public internet exposure. Second, Private Link connections can only be initiated by the service consumer, protecting them from unwanted communication. Third, Private Link supports hybrid cloud migrations by letting on-premises resources connect to AWS endpoints over AWS Direct Connect or a VPN. Because AWS's network meets strict security and compliance standards, Private Link helps organizations keep sensitive data off the public internet, supporting regulatory compliance and enhancing overall security. AWS Private Link is a powerful solution for securely connecting services across Amazon Web Services, or AWS, without exposing traffic to the public internet. Let us break down how Private Link architecture works for both service providers and consumers. On the provider side, organizations first deploy the AWS resources needed for their service. Next, they set up a network load balancer or gateway load balancer to front-end these resources. Once the load balancer is tested, the provider creates a Private Link service endpoint and grants access to specific AWS accounts, users, or roles. For consumers, connecting is straightforward. They create a virtual private cloud or VPC endpoint in their own AWS environment, which links directly to the provider's Private Link service.
This setup keeps all traffic private and secure within AWS. Service providers control access using permissions and acceptance settings. If acceptance is required, providers must manually approve each connection request, even if permissions are granted. If not required, connections are automatically accepted for authorized users. Private DNS names make connections easier. Providers specify a friendly, fully qualified domain name, or FQDN, and consumers enable this option for seamless private access, no Route 53 private hosted zone needed. AWS Private Link enables private, secure access to services hosted on Amazon Web Services, or AWS, without exposing traffic to the public internet. This is especially useful for organizations needing to connect on-premises users or applications to AWS resources. Private link services can be accessed from on-premises environments using AWS Direct Connect or Virtual Private Network, or VPN, connections. For organizations with multiple virtual private clouds, or VPCs, across regions, private link endpoints can be deployed in each VPC or centralized in a network hub account. There are important service quotas to consider. By default, each VPC supports up to 50 combined interface and gateway load balancer endpoints, but this can be increased if needed. Gateway VPC endpoints are limited to 20 per region, and this quota is also adjustable. Every private link endpoint automatically publishes metrics to Amazon CloudWatch at 1-minute intervals, with no extra cost. These metrics help organizations monitor performance and ensure their private link connections are operating smoothly. Key metrics include active connection for concurrent connections, bytes processed for data exchanged, new connections for connection counts, packets dropped for dropped packets, and RST packets received for reset packets, all helping diagnose and optimize private link performance. AWS Network Firewall is a fully managed service designed to make network-level protection simple for your Amazon Virtual Private Clouds, or VPCs. With no infrastructure to manage, you can deploy and set up robust security in just a few clicks directly from the AWS console. One of the standout features of AWS Network Firewall is its flexibility in defining firewall rules. This allows you to exercise fine-grained control over your network traffic, helping you block or stop unwanted connections efficiently. You can even import existing rules written for common open-source platforms, making it easy to leverage your current security investments. AWS Network Firewall supports integration with third-party intelligence feeds, including those from AWS partners. For centralized management across your AWS organization, it works seamlessly with AWS Firewall Manager. This integration ensures you can manage all your network firewalls efficiently, regardless of your deployment model. Technical use cases for AWS Network Firewall include inspecting traffic between VPCs, filtering outbound traffic, securing AWS Direct Connect and VPN traffic, and filtering internet-bound traffic. This makes it a versatile solution for a wide range of network security needs within AWS environments. AWS Network Firewall comes packed with powerful features designed to secure your cloud environment. Let's break down the key capabilities that make this service a robust choice for network protection. First, AWS Network Firewall is fully managed, highly available, and automatically scales to meet your needs. With a service level agreement, or SLA, guaranteeing 99.99% uptime, you can trust your firewall to be reliable and resilient. Next, AWS Network Firewall offers granular policy controls through its stateful firewall, web filtering, and intrusion prevention system, or IPS. The stateful firewall remembers session connections, enabling precise filtering beyond just TCP and UDP traffic. Web filtering supports both unencrypted and encrypted traffic using server name indication, or SNI.
The intrusion prevention system inspects real-time network traffic at the application layer, protecting against vulnerabilities and brute force attacks. Central management and visibility are built in. You can manage security policies across all your applications, virtual private clouds, or AWS organizations with aggregated compliance views, automated remediation, and detailed alerts and flow logs for every traffic event. Rule management is flexible, supporting both in-house and third-party rules. AWS Network Firewall integrates with a diverse ecosystem of partners, allowing you to leverage managed threat intelligence feeds and send security event data to third-party analytics solutions. With these features, AWS Network Firewall delivers comprehensive, customizable, and scalable protection for your cloud workloads.
When it comes to securing your AWS environment, understanding the differences between firewalls, security groups, and network access control lists is essential. Each tool serves a unique purpose in protecting your cloud resources. Security groups, often called SGs, act as virtual firewalls for AWS instances. They are not limited to just EC2 instances, but also protect AWS managed services that use instances behind the scenes. Security groups allow you to set detailed rules for both inbound and outbound traffic. By default, all outbound traffic is permitted, but you can restrict specific types if needed. Security groups are stateful, meaning if outbound traffic is allowed, the corresponding inbound response is automatically permitted. Network access control lists, or NACLs, operate at the subnet level, protecting the network rather than individual instances. NACLs help manage access to public and private subnets within a virtual private cloud, or VPC. They use a different set of rules and, by default, allow all traffic. However, NACLs can be complex for those unfamiliar with them. AWS Network Firewall offers advanced protection for your VPC network traffic. It supports alerting, logging, application traffic handling, and integrates with AWS Web Application Firewall and AWS Shield through AWS Firewall Manager. Choose AWS Network Firewall for comprehensive management, or use NACLs for simpler, set-and-forget VPC security. Understanding these tools helps keep your AWS environment secure. Let's explore the 3 most common AWS Network Firewall deployment models: distributed, centralized, and a combined approach. Each model offers unique benefits and trade-offs, depending on your organization's security needs and network architecture. In the distributed model, AWS Network Firewall is deployed into each individual virtual private cloud, or VPC, that requires protection. Each firewall can have its own policy or share a common set of roles. This approach limits misconfiguration risks, but increases management overhead and cost, as every VPC needs its own firewall. The centralized model routes all network traffic through a single VPC for inspection. This requires an AWS Transit Gateway, which acts as a network hub connecting VPCs and on-premises networks. Centralized deployment simplifies management, but introduces a medium risk of misconfiguration and a different cost structure. The combined model uses both distributed and centralized approaches. Firewalls are deployed in individual VPCs and a central inspection VPC. This model supports both VPC to VPC and VPC to internet traffic flows, offering flexibility and low risk of misconfiguration. Consider traffic flow support, prerequisites, management complexity, source IP visibility, and cost when choosing a deployment model. AWS Network Firewall is highly available and scalable, but always deploy endpoints only where needed. As your cloud networks expand, managing security across multiple environments can quickly become overwhelming. That is where AWS Firewall Manager steps in, offering a centralized way to simplify and streamline network security, especially when working with AWS network firewall deployments. AWS Firewall Manager lets you manage firewall rules and security policies across all your accounts and applications, fully integrated with AWS organizations. With just a few clicks, you can update rules, respond to security events, and ensure consistent protection everywhere. This tool is not limited to AWS Network Firewall, but for our focus, it makes deploying and managing AWS Network Firewall much easier. As your team faces the challenge of maintaining security and compliance controls, AWS Firewall Manager brings everything together, from auditing to remediation, making large-scale management efficient and less daunting. Before deploying AWS Firewall Manager, there are a few prerequisites. Your company must be part of an AWS organization with all features enabled. You need to delegate one AWS account as the firewall administrator. AWS Config must be enabled for all accounts to detect new resources, and AWS Resource Access Manager should be active to modify firewall configurations. With AWS Firewall Manager, network security becomes simpler, more scalable, and easier to manage, empowering your team to stay secure as your cloud environment grows. When designing your cloud architecture, understanding inter- and intra-regional communication is essential. These concepts determine how your resources interact within a region and across different regions in Amazon Web Services, or AWS. Intra-regional communication happens when traffic stays within a single region. For example, if you deploy two EC2 instances in different subnets but within the same region, they can communicate automatically. This traffic remains encrypted and travels on the AWS backbone, even if it crosses data centers within that region. Interregional communication involves sending traffic between resources in different regions. Since most AWS services, including virtual private clouds or VPCs, are regional, you must consider how to connect resources across regions. This often requires additional configuration in resources. Sometimes you need to deploy resources in multiple VPCs for reasons like isolation or multi-region deployments. By default, VPCs cannot communicate with each other. To enable communication, you can use VPC peering, transit gateways, or customer-managed site-to-site virtual private networks, or VPNs. VPC peering and transit gateways keep your traffic on the AWS backbone, enhancing security. Customer-managed site-to-site VPNs route traffic over the internet but offer more control over security protocols. Most organizations use a mix of these options. Virtual Private Cloud Peering, or VPC peering, is a powerful way to connect two VPCs, whether they are in the same AWS region or across different regions. It creates a single routing domain for seamless communication. While site-to-site virtual private networks, or VPNs, can also connect VPCs, they come with significant drawbacks. You must manage at least one virtual appliance, ensure its high availability, and pay for its operation. Plus, your data travels over public networks, increasing risk and potential delays. VPC peering eliminates most of these issues. There's no device to manage, no single point of failure, and no bandwidth bottlenecks. Traffic always stays on the secure AWS backbone and is encrypted. There is no charge for the peering connection itself, only for data transferred. Remember, VPCs must have non-overlapping IP ranges to peer. Peered VPCs are non-transitive, so direct connections are needed between each pair. Peered VPCs cannot share internet or virtual private gateways. VPC peering is ideal for a small number of VPCs.
As your network grows and becomes more complex, consider using AWS Transit Gateway for easier management and scalability. Transit gateways are a powerful alternative to virtual private cloud peering, or VPC peering, for connecting multiple VPCs. Instead of creating individual peering connections, each VPC attaches to a central transit gateway, forming a hub-and-spoke network design. Transit gateways operate as a regional service. For example, VPCs in the EU West 2 region must connect to a transit gateway in that same region. To enable communication between VPCs in different regions, you can peer transit gateways across regions, allowing seamless inter-regional connectivity. Using a transit gateway offers several advantages over VPC peering. You can share site-to-site VPN or direct connect connections and a single route to the internet. Transit gateways are highly scalable, supporting up to 5,000 attachments per gateway compared to just 50 with VPC peering. However, transit gateways come with higher costs. You are charged per hour for each attachment and for every gigabyte of data processed. Despite this, data between VPCs attached to a transit gateway remains on the Amazon Web Services backbone. Transit gateways support multiple route tables, giving you granular control over traffic flow. They also enable equal-cost multipath routing for active-active on-premises connectivity and support software-defined wide-area network connections using AWS Transit Gateway Connect. When your resources in an Amazon Web Services Virtual Private Cloud, or AWS VPC, need to connect to services like Amazon S3 or DynamoDB, they often use public endpoints. This means your data travels over public networks, which can be less secure. Gateway endpoints offer a solution for Amazon S3 and DynamoDB. When you set up a gateway endpoint, a new route is added to your VPC's route tables. Any traffic matching the destination prefix list, such as PL7CA54015, is securely routed through the AWS backbone, keeping your data off public networks. For other AWS services and third-party connections, interface endpoints are used. These create elastic network interfaces, or ENIs, in your subnets. Traffic is routed directly to the ENI's IP address, providing secure private connectivity within your VPC. Gateway endpoints are free, but interface endpoints incur hourly and per gigabyte charges. Gateway endpoints are only accessible within the VPC, while interface endpoints can be accessed from any source that can route traffic to the subnet. You can also advertise your own services through the AWS backbone. By creating an endpoint service, you control which AWS accounts, IAM users, or roles can connect, ensuring secure and private access for your customers. Connecting on-premises environments to the AWS cloud. Welcome to this course on connecting on-premises environments to the Amazon Web Services cloud. This course is designed to support your journey toward the AWS Certified Advanced Networking Specialty Certification, focusing on essential networking concepts and services. Course objectives. Our main goal is to provide a high-level introduction to the tools, technologies, and services used to connect on-premises environments to the AWS cloud. You will learn about AWS Direct Connect and Virtual Private Networks, or VPNs, and how encryption is used to secure traffic as it moves across these connections. We will also introduce AWS routing fundamentals and industry-standard routing protocols, such as Border Gateway Protocol, or BGP. Key topics covered. Throughout this course, you will explore the integration of AWS networking services, security best practices, and the nuances of hybrid networking architectures. Each concept will be explained and reinforced from the ground up, ensuring you gain a solid understanding. Together with other courses in this learning path, you will cover all the key tools, technologies, and concepts from the AWS Certified Advanced Networking Specialty Exam Guide. Who should take this course? This course is ideal for those with experience designing, implementing, and operating complex AWS and hybrid networking architectures, especially if you are preparing for the AWS Certified Advanced Networking Specialty Exam. Many organizations start their cloud journey cautiously, often by expanding storage with Amazon's Simple Storage Service, or S3, to support long-term data retention. This careful approach allows businesses to validate how AWS can address their unique challenges before fully committing to the cloud. Once initial use cases are proven, organizations may deploy Amazon Elastic Compute Cloud, or EC2, instances and look to connect these with their on-premises data centers. This hybrid setup enables EC2 instances to access resources like Active Directory domains, private domain name system zones, and internal databases. To securely connect these environments, companies often use an AWS Site-to-Site Internet Protocol Security, or IPsec, virtual private network tunnel. They can choose between a virtual private gateway, which connects to a single virtual private cloud, or a transit gateway, which links multiple virtual private clouds within a region. While these VPN solutions are quick and easy to set up, they have limitations. Each VPN tunnel supports a maximum bandwidth of 1.25 gigabits per second and relies on the public internet, which can result in unpredictable performance. To overcome these challenges, organizations turn to AWS Direct Connect. This service provides dedicated, high-bandwidth connectivity, ensuring consistent performance for latency-sensitive applications and maximizing the benefits of AWS. AWS Direct Connect offers organizations a dedicated high-speed and low-latency connection to Amazon Web Services by bypassing the public internet. This service is ideal for businesses needing reliable and consistent network performance when accessing AWS resources, but it is not a fully managed end-to-end connectivity solution. When you order AWS Direct Connect, you are granted access to a 1, 10, or 100 gigabits per second network port at a Direct Connect location, also known as a DX location. However, you are responsible for connecting your data center to this port, typically by working with a network partner. Unlike a virtual private network, or VPN, Direct Connect requires physical cabling, which can take weeks or months to install. Before ordering, ensure your network supports single-mode fiber and the correct transceivers for your chosen speed. Ports must be manually set to the correct speed and full duplex mode. All devices must support 802.1q VLAN encapsulation, and your router must support Border Gateway Protocol, or BGP, with BGP MD5 authentication. Asynchronous bidirectional forwarding detection, or BFD, is available but must be configured on your network. AWS Direct Connect supports both Internet Protocol version 4 and 6 and allows Ethernet frame sizes up to 9,023 bytes. When considering AWS Direct Connect, one of the first questions that comes up is, how much does it cost? The answer, as with many technology services, is that it depends on several factors. AWS Direct Connect pricing is based on two main elements: port hours and data transfer out, or DTO. Port hours are the amount of time your Direct Connect port is provisioned, similar to how you pay for an on-demand EC2 instance. Even if no data is moving, you are still billed for the port being available. Data transfer out is the total data sent from AWS to external destinations, charged per gigabyte. Pricing varies depending on your AWS region and the specific Direct Connect location you use. To estimate your costs, you can use the AWS pricing calculator.
For example, a single 1 gigabit dedicated connection in Northern Virginia running at full utilization costs about $219 per month for port hours. If you transfer 100 terabytes of data out, that adds approximately $2,048 per month. Understanding your application's usage patterns is crucial. Both port hours and data transfer can significantly impact your monthly bill, so careful planning is essential for accurate cost estimation. Many organizations begin their cloud journey with simple solutions like Amazon S3 for backups. But as production workloads move to the cloud, a reliable connection between on-premises data centers and AWS becomes essential. While VPN tunnels using AWS virtual private gateways or transit gateways are quick to set up, they rely on the public internet, which can be unpredictable and limited to 1.25 gigabits per second. AWS Direct Connect solves this by providing a dedicated, high-speed, low-latency connection from your business location to AWS, bypassing the public internet entirely. This setup involves your business site, an AWS region, and a Direct Connect location, which is a regional colocation facility with AWS-managed routers. Before ordering AWS Direct Connect, ensure your network meets several requirements. Use single-mode fiber and appropriate transceivers. Disable auto-negotiation and set full duplex. Support 802.1q VLAN encapsulation, and have a router that supports Border Gateway Protocol, or BGP, with BGP MD5 authentication. Direct Connect also supports asynchronous bidirectional forwarding detection, or BFD, both IP version 4 and IP version 6, and Ethernet frame sizes up to 9023 bytes. AWS Direct Connect costs are based on port hours, which is the time your port is provisioned, and data transfer out, charged per gigabyte. AWS Direct Connect offers a robust, dedicated solution for connecting your data center to AWS, supporting demanding workloads with reliability and speed. To connect your on-premises network to Amazon Web Services using AWS Direct Connect, you need at least one virtual interface, or VIF. A VIF enables Border Gateway Protocol, or BGP, peering between your router and AWS, allowing secure traffic exchange. There are 3 types of VIFs. Public VIFs provide access to AWS public services like Amazon Simple Storage Service and Amazon Simple Notification Service, using public IP addresses. Private VIFs connect directly to resources in your Amazon Virtual Private Cloud, or VPC, using private IP addresses. Transit VIFs link multiple VPCs across accounts and regions through a transit gateway and a direct connect gateway. Each VIF requires a name, an owner account, a unique virtual local area network, or VLAN ID, and an address family, either Internet Protocol version 4 or version 6. You must also specify a BGP Autonomous System Number, or ASN, and set a BGP MD5 authentication key for secure connections. Public VIFs are ideal for high-speed access to AWS public services. Private VIFs enable direct connectivity to VPC resources. Transit VIFs simplify complex hybrid cloud networks. Always use clear naming and proper ASN ownership for best results. When setting up AWS Direct Connect, or DX, customers often wonder if they can request multiple connections in one or more DX locations to boost resiliency. The answer is yes, and AWS has made this process straightforward. Ordering connections and the Resiliency Toolkit. Using the AWS Management Console, customers can choose between Classic and Connection Wizard ordering types. The Connection Wizard launches the AWS Direct Connect Resiliency Toolkit, which helps organizations design resilient architectures that align with their Service Level Agreement, or SLA, objectives. Resiliency Models Explained.
The Resiliency Toolkit offers three models: maximum resiliency, which creates multiple DX connections in multiple locations; high resiliency, which creates a single DX connection in multiple locations; and development and test, which creates multiple DX connections in a single location. Understanding link aggregation groups, or lags. Multiple DX connections within one location can be grouped as a link aggregation group, or lag. Lags combine the bandwidth of several physical connections, so four 1 gigabit connections act as a single 4 gigabit connection. Key lag considerations and limitations. All connections in a lag must be the same speed and in the same location. Lags improve performance and provide some resiliency, but do not protect against an entire DX location failure. Since November 2018, the AWS Transit Gateway, or TGW, has transformed how organizations connect and scale their cloud networks. But what makes it so essential for modern AWS environments? Before Transit Gateway, connecting virtual private clouds, or VPCs, relied on VPC peering. This created one-to-one non-transitive links. For example, VPC A could talk to VPC B and VPC C, but B and C could not communicate directly without their own connection. As networks grew, managing countless peering connections became complex and unsustainable. The AWS Transit Gateway introduced a hub-and-spoke model, acting as a central hub for routing traffic between VPCs, on-premises data centers, and remote offices. This architecture simplifies network management and supports connections across multiple AWS accounts and regions. Transit Gateway networks are encrypted and do not traverse the public internet. Each transit gateway supports up to 5,000 attachments and 50 peering connections. With Direct Connect and Transit Virtual Interfaces, or VIFs, organizations can securely link on-premises networks to AWS, even across regions. Imagine 3 data centers, each using Direct Connect and Transit VIFs, all communicating seamlessly with AWS resources in any region through the Transit Gateway network. AWS Direct Connect is a dedicated network service that links your on-premises environment directly to Amazon Web Services, or AWS. This connection offers consistent, low-latency performance and enhanced security compared to standard internet connections. To get started, request a Direct Connect connection at an AWS Direct Connect location. AWS allocates support, and you complete a Letter of Authorization Customer Facility Access Form, or LOA-CFA. This form allows support staff to connect your equipment to the AWS port, establishing physical connectivity. Once connected, you must create at least one virtual interface, or VIF. A VIF enables Border Gateway Protocol, or BGP, peering between your router and AWS. There are 3 types: public, private, and transit, each supporting different AWS resources and network architectures. For advanced setups, the AWS Direct Connect Resiliency Toolkit offers models like maximum resiliency and high resiliency. Link aggregation groups, or lags, combine multiple connections for greater bandwidth and performance, but do not protect against entire location failures. The AWS Transit Gateway simplifies global network management with the hub-and-spoke model. Each transit VIF supports up to 3 transit gateways, and a single Direct Connect can support up to 50 public and private VIFs, enabling scalable, flexible connectivity across regions. This course introduces you to the IPsec Protocol Suite, a foundational technology for securing network communications. You will learn what IPsec is, why it is important, and how it enhances both networking and security in modern environments. We will break down the individual components of IPsec, including authentication headers, encapsulating security payloads, and security associations.
The course covers Internet Key Exchange, or IKE, Phase 1 and Phase 2, as well as the differences between transport mode and tunnel mode, ensuring you understand each element's role. Explore real-world scenarios where IPsec is especially useful, such as connecting remote networks securely. We will also discuss the limitations of IPsec, highlighting potential issues and considerations to keep in mind when deploying these tunnels. Discover how Amazon Web Services, or AWS, implements IPsec. You will be introduced to key virtual private cloud, or VPC, components like the Virtual Private Gateway, Customer Gateway, and VPN connection, and see how they work together. Amazon Web Services, or AWS, lets you securely extend your on-premises network into the cloud using a Virtual Private Cloud, or VPC, and an IPsec VPN connection. This setup protects your data as it travels between your corporate network and AWS. IPsec, which stands for Internet Protocol Security, is a framework of protocols that ensures data confidentiality, integrity, and authentication as it moves across networks. It operates at the network layer, making it transparent to applications and requiring no changes to your software. To connect your network to AWS, you deploy a virtual private gateway on the AWS side and a customer gateway on your side. Each VPN connection creates two redundant IPsec tunnels for high availability, automatically routing traffic if one tunnel goes down. IPsec uses two main protocols: Authentication Header, or AH, for authentication and integrity, and Encapsulating Security Payload, or ESP, for encryption and authentication. Encryption algorithms like AES and hashing algorithms like SHA provide robust security for your data in transit. AWS VPNs are quick to set up and cost 5 cents per connection hour, plus data transfer fees. However, they only support tunnel mode and do not support IPv6 traffic. So, consider your bandwidth and protocol needs before deploying. When connecting your office network to Amazon Web Services, or AWS, keeping your data secure as it travels is essential. Let us break down the encapsulation protocols that protect your information during hybrid network connectivity. You can connect to AWS using AWS-managed site-to-site virtual private networks, or VPNs, customer-managed site-to-site VPNs, and AWS Direct Connect. No matter which method you choose, your data must be protected by strong authentication, integrity checks, and encryption. AWS-managed VPNs use pre-shared keys or digital certificates for authentication, hashing algorithms like the Secure Hash algorithm for integrity, and Internet Protocol Security, or IPsec, for encryption. AWS recommends managed VPNs, but customer-managed VPNs allow you to use custom algorithms. IPsec is an open standard in the Internet Protocol version 4 suite. It secures AWS-managed VPNs using protocols like authentication headers for data integrity, encapsulating security payload for confidentiality, and Internet Security Association and Key Management Protocol for key exchange. Two endpoints negotiate security settings in 2 phases using Internet Key Exchange, or IKE. AWS Direct Connect does not encrypt traffic by default. To secure data, you can run a VPN over Direct Connect or enable MACsec, known as MACsec. Understanding these protocols ensures your data remains confidential, integral, and authenticated as it moves between your network and AWS. Encryption is a key part of securing AWS-managed site-to-site virtual private networks, or VPNs. To set up a VPN, you need a virtual private gateway, or transit gateway, a customer gateway, and a VPN connection.
During VPN connection setup, you configure Internet Protocol Security, or IPsec settings. AWS automatically creates 2 IPsec tunnels, each with customizable encryption options. You can select Phase 1 and Phase 2 encryption algorithms like Advanced Encryption Standard 256 or AES 256 and remove others to enforce strict protocols. Both ends of the VPN must support the same encryption protocol for a successful connection. You also choose integrity algorithms and Diffie-Hellman groupings for secure key exchange. Diffie-Hellman allows keys to be negotiated during session setup, and higher group numbers mean stronger encryption. You can repeat these configurations for Tunnel 2, giving you full control over your VPN's security. After configuring both tunnels, you can download a configuration file tailored to your on-premises device, such as those from Cisco systems. This file contains all necessary IPsec details, ensuring your site-to-site VPN is secure and ready to use. When using AWS Direct Connect, it is important to remember that, unlike site-to-site VPN connections, Direct Connect does not encrypt your traffic by default. If you need encryption, you have 2 main options. The first option is MACsec, or MAC Security. MACsec provides confidentiality, integrity, and origin authenticity for your data. However, MACsec is only available for dedicated Direct Connect connections at either 10 gigabits per second or 100 gigabits per second. It is not supported on hosted or 1 gigabit per second connections. You will also need compatible on-premises devices and support from your last-mile provider. MACsec operates at Layer 2 and uses hardware encryption, which means you get near-line rate speeds and full bandwidth. The second option is to enable a VPN connection over your Direct Connect link. This uses a public virtual interface, or VIF, to connect to AWS public endpoints. You then create a VPN connection with your AWS Virtual Private Gateway or Transit Gateway, combining the security of IPsec with the low latency and high bandwidth of Direct Connect. Remember, MACsec is faster than IPsec and allows full bandwidth, while VPNs offer encryption for all Direct Connect types. Choose the method that best fits your security and performance needs. When you create a virtual private cloud or VPC in Amazon Web Services, an implicit router is automatically set up for you. This router connects to each subnet using the first IP address of the subnet, even though you cannot see it directly. Each VPC comes with a default routing table. This table includes a local route, which cannot be changed or deleted. The local route allows all resources within the VPC, such as EC2 instances in different subnets, to communicate with each other using the VPC's assigned IPv4 CIDR block, like 10.0.0.0.0/16. To enable EC2 instances in public subnets to access the Internet, you must attach an Internet gateway to your VPC. Then, update the routing table to add a default route, 0.0.0.0/0, pointing to the Internet gateway. This sends all non-local traffic to the Internet. For private subnets, a NAT gateway is used. Deploy the NAT gateway in a public subnet, associate private subnets with a new routing table, and add a default route to the NAT gateway. This allows private instances to access the Internet securely. Every VPC has a main route table, which new subnets use by default. It is best practice to keep only the local route here. For IPv6 traffic from private subnets, use an egress-only Internet gateway, which works like a NAT gateway, but for IPv6 addresses. Let us break down static and dynamic routing in Amazon Web Services, or AWS.
and see how they help connect your on-premise networks to the cloud. With static routing, you manually update routing tables with every network route. If you add a new network, you must enter its details yourself. This approach gives you control, but it is time-consuming and can be error-prone, especially as your network grows. Dynamic routing uses protocols that automatically exchange network information between routers. In AWS, the Border Gateway Protocol, or BGP, is used for dynamic routing. BGP enables routers to share updates, so when your network changes, routes are updated automatically. Your on-premise routers must support BGP if you want dynamic routing with AWS. Organizations often use hybrid environments, combining on-premise and AWS resources. AWS offers site-to-site VPNs and Direct Connect for hybrid connectivity. Site-to-site VPNs support both static and dynamic routing, while Direct Connect requires dynamic routing. Enabling route propagation in AWS route tables allows static prefixes from VPN connections to be written automatically, simplifying management even with static routing. Choose static routing from manual control or dynamic routing with BGP for automation and scalability in your AWS hybrid network. With static routing, you manually update routing tables with every network route. If you add a new network, you must enter its details yourself. This approach gives you control, but it is time-consuming and can be error-prone, especially as your network grows. Dynamic routing uses protocols that automatically exchange network information between routers. In AWS, the Border Gateway Protocol, or BGP, is used for dynamic routing. BGP enables routers to share updates, so when your network changes, routes are updated automatically. Your on-premise routers must support BGP if you want dynamic routing with AWS. Organizations often use hybrid environments, combining on-premise and AWS resources. AWS offers site-to-site VPNs and Direct Connect for hybrid connectivity. Site-to-site VPNs support both static and dynamic routing, while Direct Connect requires dynamic routing. Enabling route propagation in AWS route tables allows static prefixes from VPN connections to be written automatically, simplifying management even with static routing. Choose static routing for manual control, or dynamic routing with BGP for automation and scalability in your AWS hybrid network. Navigating AWS networking can be complex, especially when connecting multiple virtual private clouds, or VPCs, and on-premises networks. Each VPC is isolated by default, so connecting them securely requires extra steps. While VPC peering and VPNs are common solutions, they become difficult to manage as the number of networks grows. For example, connecting 5 VPCs directly would require 10 separate peering connections, quickly increasing complexity. AWS Transit Gateway is Amazon's answer to this challenge. Acting as a regional network transit hub, it lets you interconnect hundreds of VPCs and on-premises networks without the hassle of managing countless individual connections. Transit Gateway is a managed service, so AWS handles scaling and infrastructure. You attach VPCs, VPNs, or Direct Connect gateways to it and use route tables to control traffic flow. It operates at Layer 3, routing packets based on destination IP addresses. Transit Gateway simplifies network architecture, supports multiple route tables for flexible traffic control, and scales automatically. However, there are limits. 5 transit gateways per region, 5 attachments per VPC, and a maximum bandwidth of 50 gigabits per second per connection. The OSI model and TCP/IP protocol suite. Welcome! This course on the OSI model and the TCP/IP protocol suite designed to support your preparation for the AWS Certified Advanced Networking Specialty Certification. Whether you are new to AWS networking or looking to deepen your expertise, you are in the right place. This course provides a high-level introduction to the OSI model and the TCP/IP protocol suite. Our goal is to help you understand the foundational networking models as well as practical concepts like building and configuring jumbo frames. By the end, you will be ready to tackle networking questions on the updated AWS Certified Advanced Networking Specialty exam. We will explore the OSI and TCP/IP networking models, focusing on how they relate to AWS networking services. You will learn about jumbo frames and their configuration. The course concludes with an in-depth review of the IPv4 protocol, including classless inter-domain routing or CIDR, IPv4 reserved addresses, subnetting, and addressing modes such as unicast and multicast. This course is ideal for those with experience designing, implementing, and operating complex AWS and hybrid networking architectures, especially if you are preparing for the AWS Certified Advanced Networking Specialty exam. All AWS cloud concepts will be explained from the ground up, ensuring you are fully prepared to sit the exam. Let's get started.
The Open Systems Interconnection Model, or OSI model, is a framework introduced in 1984 by the International Standard Organization. It defines how different networking protocols interact in a stack of 7 layers, making it easier to understand and design networks. The TCP/IP model, also known as the Internet Protocol Suite, is the foundation for most modern networks, including the Internet. Developed in the 1970s by the United States Department of Defense, it predates the OSI model. Unlike the OSI model's 7 layers, the TCP/IP model has just 4. These are the application layer, transport layer, internet layer, and network layer. The application layer combines the OSI's application, presentation, and session layers, while the network layer merges the physical and data link layers. As data moves down the TCP/IP stack, each layer adds its own header. The application layer handles user data. The transport layer creates segments or datagrams. The internet layer forms packets with IP addresses, and the network layer produces frames with MAC addresses for local delivery. Protocols like HTTP, SMTP, and FTP operate at the application layer. The Transmission Control Protocol, or TCP, ensures reliable delivery, while the User Datagram Protocol, or UDP, prioritizes speed. The Internet Protocol, or IP, manages logical addressing, and Ethernet handles physical connections. Understanding TCP/IP is essential, as it powers everything from web browsing to email. Its layered approach and robust protocols make global communication possible, forming the backbone of today's interconnected world. Let us break down jumbo frames and why they matter for your network performance. The maximum transmission unit, or MTU, is the largest packet size, measured in bytes, that a network connection can handle. The bigger the MTU, the more data you can send in a single packet. Standard Ethernet frames typically support a 1500-byte MTU, which is the maximum size for most internet connections. Jumbo frames, on the other hand, can support up to 9,000 bytes, allowing you to send up to 6 times more data in one go. This is especially useful for high-performance environments. Because Ethernet frames have a fixed size header, sending larger frames means less overhead and more efficient data transfer. Jumbo frames are ideal for dedicated private networks, server clustering, backups, and distributed file systems like the Network File System, or NFS. Amazon EC2 instance types such as C3, M4 and R4 support jumbo frames for enhanced throughput. However, jumbo frames are not suitable for every scenario. Applications sensitive to latency, like voice over IP, may experience delays. Always ensure all network equipment supports the larger MTU before enabling jumbo frames. Let us demonstrate the impact of jumbo frames in a cloud environment. We will compare two network paths between virtual machines, one using a standard maximum transmission unit, or MTU, of 1500 bytes, and another using jumbo frames with an MTU of 9000 bytes. Our setup involves two virtual private clouds, or VPCs, each with two subnets. We launch an EC2 T2.micro instance in each subnet, and each instance has two elastic network interfaces, or ENIs. The first ENI, ETH0, is set to an MTU of 1500, while the second, ETH1, uses an MTU of 9000. Policy-based routing ensures traffic flows through the correct interface. We used a CloudFormation template to build this environment. After setup, we SSH into the receiver instance and start a netcat listener on port 10000. On the sender instance, we run scripts to send exactly 1 megabyte of data, first over ETH0 with standard frames, then over ETH1 with jumbo frames. Packet captures are taken for analysis. The results are clear. Transferring 1 megabyte with jumbo frames results in significantly fewer packets and higher throughput compared to standard frames. This demonstrates the efficiency and performance benefits of using jumbo frames for large data transfers in cloud networks. IPv4, or Internet Protocol Version 4, is the backbone of Internet addressing. Standardized in the early 1980s, it uses a 32-bit binary scheme, providing about 4.3 billion unique addresses. This logical addressing operates at the Internet layer of the TCP/IP model. An IPv4 address consists of 32 binary bits, grouped into 4 octets separated by dots. Each octet ranges from 0 to 255 in decimal, making addresses like 192.168.10.1 easy to read. This format is called dotted decimal notation. Originally, IPv4 used address classes A, B, and C to divide networks and hosts, but this system was inefficient. In 1993, classless interdomain routing, or CIDR, replaced it, allowing flexible subnet masks and more efficient use of address space. Certain IPv4 ranges are reserved for special purposes. For example, 127.0.0.1 is for loopback testing, while 10.0.0.0, 172.16.0.0, and 192.16.0.0 are private addresses, not routable on the public internet. Subnetting divides a network into smaller segments, improving performance and security. It uses subnet masks like 255.255.255.0 to define network and host portions within an address. The OSI model and TCP/IP protocol suite. Welcome to this course on Content Distribution and Domain Name System, or DNS, designed to support your preparation for the AWS Certified Advanced Networking Specialty Certification. This course is part of a comprehensive learning path to help you master AWS networking concepts. Our main goal is to provide a high-level introduction to design patterns for content distribution and DNS from an Amazon Web Services networking perspective. You will learn how to leverage Amazon CloudFront for content distribution networks and use Route 53 to design solutions that address public, private, and hybrid DNS requirements. We will explore Route 53 features that help route end users to internet applications efficiently.
Throughout the course, you will gain insights into integrating AWS networking services and understanding AWS security best practices. All AWS cloud concepts introduced here will be explained and reinforced from the ground up, ensuring a solid foundation. This course is ideal for those with experience designing, implementing, and operating complex AWS and hybrid networking architectures. If you are preparing for the updated AWS Certified Advanced Networking Specialty exam, this course will help ensure you are fully prepared. Amazon CloudFront is Amazon Web Services' globally scalable and fault-tolerant content delivery network, or CDN. It integrates seamlessly with other AWS services, making it easy to distribute both static and dynamic content to users around the world. When a user requests content, CloudFront routes the request to the nearest AWS edge location. These edge locations are deployed in major cities and populated areas globally. By serving cache data from the closest edge, CloudFront significantly reduces latency and speeds up content delivery, whether your website is hosted on Amazon S3 or EC2 instances. CloudFront uses distributions to control what data is delivered and where. There are two main types: web distributions for static and dynamic content, and RTMP distributions for streaming media using the Adobe Flash RTMP protocol. RTMP distributions require the source data to be stored in an S3 bucket. For added security, you can use an Origin Access Identity, or OAI, to restrict S3 bucket access. CloudFront also offers customizable caching policies, SSL certificate support, and integration with AWS's Web Application Firewall for enhanced protection. Amazon CloudFront brings your content closer to users, improving speed and security while reducing latency through its global network of edge locations. Amazon CloudFront is a content delivery network service from Amazon Web Services, or AWS, designed to deliver your website's content to users worldwide with low latency and high speed. Its main purpose is caching content closer to your users. When your website is hosted in one region, like EU West 2, users far away, such as in the United States or Australia, may experience higher latency. CloudFront solves this by storing copies of your content at global edge locations, so users everywhere get faster access. To use CloudFront, you create a distribution and select your content's origin, such as an Amazon S3 bucket or an application load balancer. You can customize settings like protocols, cache duration, price class, and even use your own domain name with a digital certificate. CloudFront uses 3 caching layers: edge locations, regional edge caches, and AWS Origin Shield. This multi-layered approach improves cache hit ratios, reduces load on your origin servers, and boosts network performance by keeping content closer to users. CloudFront offers robust security, including encrypted SSD storage, signed URLs, AWS Web Application Firewall, or WAF, geo-restrictions, and integration with identity and access management. Monitoring is available through Amazon CloudWatch, AWS CloudTrail, and real-time logs. Amazon CloudFront is a powerful content delivery network that helps cache and secure your web content. Let us look at 2 common patterns for using CloudFront to boost performance and security. First, you can set up CloudFront with an application load balancer as the origin. Update your Route 53 DNS records so your website's friendly name points to CloudFront, not directly to the load balancer. To secure access, configure CloudFront to add a custom HTTP header to each request. Then, set your load balancer to only forward requests containing this header, returning a 403 error for others. Use HTTPS between CloudFront and the load balancer for encryption, and regularly rotate your custom header for added security. Second,
CloudFront can cache and secure content from an Amazon S3 bucket. This reduces latency for global users and enables HTTPS using AWS Certificate Manager, or ACM. To restrict access, create an Origin Access Identity, or OAI, and update your S3 bucket policy so only CloudFront can retrieve content. This blocks direct public access, ensuring users benefit from CloudFront's security and performance. With CloudFront, you can efficiently cache and secure your content, whether your origin is an application load balancer or an S3 bucket. Amazon Route 53 is a global domain name service system from Amazon Web Services, or AWS, designed to help you register and manage domain names worldwide. With Route 53, you can easily handle domain name registration and DNS management, all through a single, reliable platform. Route 53 stands out by offering robust traffic management. It routes internet traffic to your domain's resources and uses health checks to ensure everything is working as expected. Thanks to AWS's global infrastructure and distributed DNS system, Route 53 is highly available, backed by a 100% service level agreement. You do not need to specify a region when configuring Route 53 resources, making it truly global. Routing policies in Route 53 let you control how traffic is directed, with options like failover and latency routing. The Application Recovery Controller manages failovers using integrated health checks. For virtual private clouds, or VPCs, Route 53 Resolver and DNS Firewall provide secure, managed DNS query handling. This service is ideal for architects, developers, system operators, and administrators managing domain name servers on AWS. To get started, you should meet the AWS Cloud Practitioner certification requirements. Amazon Route 53 is the domain name management service from Amazon Web Services, or AWS. It acts like the Internet's phone book, translating easy-to-remember domain names into the numerical IP addresses that computers use to communicate. When you register a domain with Route 53, it becomes the authoritative domain name system, or DNS, server for your domain. It creates a public hosted zone for internet traffic, and you can also set up private hosted zones for internal networks called virtual private clouds, or VPCs. Each hosted zone contains records. Important ones include name server, or NS, records, which identify DNS servers, and start of authority, or SOA records, which define the authoritative server for the zone. Other common records are A and AAA for mapping host names to IP addresses, MX for email servers, TXT for text information, and CNAME for mapping host names to other host names. Unique to Route 53, alias records let you map custom domain names directly to AWS resources like CloudFront distributions, Amazon S3 buckets, or Elastic load balancers, making integration seamless. When creating records, you set the name, type, value, time to live, and routing policy, which controls how DNS queries are answered, including options for health checks. Amazon Route 53 health checks are essential tools for ensuring your application's reliability. By continuously monitoring endpoints, Route 53 helps you deliver accurate responses to user queries, keeping your services available and resilient. When you set up a health check, Route 53 sends requests to your endpoint every 30 seconds. Based on the responses, it determines whether the endpoint is healthy or unhealthy. This health status directly influences which records Route 53 returns in response to user queries, ensuring only healthy endpoints are used. You can configure multiple health checks for different application tiers, allowing independent verification before considering the entire application healthy. Route 53 compares the number of healthy checks to a threshold you set. Additionally, Route 53 health checks can monitor the state of an Amazon CloudWatch alarm, adapting the health status based on the alarm state. Health checks can target endpoints by IP address or domain name using TCP, HTTP, or HTTPS protocols. For HTTP and HTTPS, you can specify a string to match in the response body, adding another layer of validation. Route 53 health checks are performed globally, and you can choose to receive notifications whenever a health check fails, helping you respond quickly to potential issues. DNS routing policies determine how queries are answered. The simple routing policy links the domain name to one or more IP addresses, randomly selecting which to use. However, it does not support health checks. Weighted routing is similar, but lets you assign a numerical weight to each IP address, favoring some over others. A weight of 0 means a record is never returned, making this policy useful for load distribution or testing new software. Weighted routing supports health checks, ensuring only healthy records are used. Geolocation routing tags records by location, such as country or continent, and returns the IP address best suited for the user's region. This helps serve customers in different languages or protect licensing rights. Geo-proximity routing, which requires Route 53's traffic flow feature, routes traffic based on distance and a bias value. Adjusting the bias shifts more or less traffic to specific endpoints, allowing fine-tuned control over regional traffic distribution. Failover routing directs traffic to a primary resource, but if a health check fails, it automatically redirects to a secondary resource. Latency routing chooses the record with the lowest latency for the user, based on AWS's latency database, ensuring faster connections. Multi-value answer routing returns up to 8 healthy IP addresses in response to a query, maximizing availability. Each DNS routing policy offers unique ways to optimize traffic, improve reliability, and deliver the best user experience based on your needs. Managing records in large, complex configurations can be challenging, especially when you have groups of resources like fleets of web servers serving the same domain. Traffic flow is designed to simplify this process, making it easier to create and maintain records efficiently. With the Traffic Flow Visual Editor, you can build complex sets of records and instantly see how they relate to each other. This tool allows you to combine multiple routing policies and health checks within a single configuration known as a traffic policy. Each traffic policy is automatically versioned, so you never have to start from scratch when changes are needed. Previous versions remain available until you choose to delete them, giving you flexibility and control. A single traffic policy can define hundreds of records, and Traffic Flow generates all these records automatically when you create a policy record. Policy records link traffic policies to specific domain or subdomain name records, and they appear in your hosted zone's record list. You can even use the same traffic policy across multiple public hosted zones, which is especially helpful when managing multiple domains with the same hosts. It is important to note that the geo-proximity routing policy is only available when you use Traffic Flow, offering advanced routing options for your configurations. Amazon Web Services Route 53 Resolver is the domain name system or DNS service designed specifically for virtual private clouds or VPCs. It seamlessly integrates with your data center, making it easier to manage DNS queries between your on-premises environment and AWS. To connect your data center DNS with AWS, you need to establish connectivity using either AWS Direct Connect or a virtual private network connection. Once connected, you configure endpoints by assigning IP addresses in each subnet that requires Route 53 Resolver access. Route 53 Resolver supports both inbound and outbound DNS queries. Inbound queries allow DNS requests from your data center to resolve domains hosted within AWS. For outbound queries, you set up conditional forwarding rules. These rules specify which domains, hosted in your data center, should be forwarded from AWS. When a query matches a rule,
Route 53 Resolver forwards the request to your data center, ensuring seamless DNS resolution across environments. Route 53 Resolver DNS Firewall is a managed service that inspects and filters DNS queries originating from your VPCs. By creating firewall rule groups, you define which domains to inspect and what actions to take. You can allow, alert, or block queries, protecting your VPC traffic. Amazon Route 53 Application Recovery Controller is designed to help you monitor and control your application's recovery across multiple availability zones, regions, and even your own data centers. It ensures your applications are always ready to recover from failures. With Route 53 Application Recovery Controller, you can define readiness checks to monitor your AWS resource configurations, capacity, and network routing policies. These checks cover resources like auto-scaling groups, Amazon EC2 instances, Amazon Elastic Block Store volumes, Elastic Load Balancers, Amazon Relational Database Service instances, and DynamoDB tables. Readiness checks confirm that your recovery environment is properly scaled and configured to take over when needed. Readiness checks work hand in hand with routing controls, allowing you to fail over an entire application based on custom conditions, such as application metrics, partial failures, increased error rates, or latency. You can also initiate failover manually. Routing controls let you shift traffic for maintenance or during real failure scenarios. And safety rules help prevent failover to an unprepared replica. A control panel is a group of routing controls for your application. Routing controls can turn traffic flow on or off to specific cells in regions or availability zones, enabling custom traffic redirection during failover or maintenance. Amazon Route 53 Application Recovery Controller empowers you to configure fine-grained failover and verification steps, supporting applications that demand very high availability. AWS Authentication, Authorization, and Access Control. Are you preparing for the AWS Certified Advanced Networking Specialty Certification? This course is designed to guide you through authentication, authorization, and access control in Amazon Web Services, or AWS, and help you master the networking concepts needed for the updated exam. Let's start by defining the essentials. Authentication is the process of verifying the identity of a user or system. Authorization determines what actions that user or system is allowed to perform. Access control refers to the policies and mechanisms that enforce these permissions. Understanding the differences between these three is crucial for anyone working with AWS networking services. AWS offers a variety of authentication mechanisms and authorization controls. Throughout this course, you'll be introduced to these tools, learning how they integrate with AWS services and support security best practices. Whether you're managing complex AWS or hybrid networking architectures, knowing how to implement these controls is key to securing your environment. By the end of this course, you'll have a solid foundation in AWS authentication, authorization, and access control. You'll be ready to tackle exam questions that require advanced knowledge and confidently approach the AWS Certified Advanced Networking Specialty Certification. Let us clear up the confusion between authentication, authorization, and access control. First, authentication is all about proving who you are. For example, when you log into your Amazon Web Services account, you provide a unique username and then verify your identity with a password. This two-step process confirms your identity. Authentication is not limited to people.
IT services, like an EC2 instance accessing Amazon S3, also use authentication by presenting identity and verification. Once authentication is complete, authorization comes into play. Authorization determines what you are allowed to do after your identity is verified. For instance, in Amazon Web Services, the Identity and Access Management Service, or IAM, assigns specific permissions to each user. Stuart might have full access to Amazon S3, while Will can only create EC2 instances. Authorization is about setting these boundaries. Access control refers to the methods used to grant or restrict access to resources. This includes mechanisms like usernames and passwords, multi-factor authentication, or IAM roles. Access control can also involve network-level restrictions, such as Network Access Control Lists, or NACLs, and security groups that filter access by IP address or port. To summarize, authentication verifies identity, authorization defines permissions, and access control enforces how access is granted. Understanding these differences is essential for effective and secure cloud resource management. Introduction to IAM. AWS Identity and Access Management, or IAM, is the service that lets you securely manage users and their access to your AWS resources. It is essential for controlling who can do what in your AWS environment. User authentication basics. When creating IAM users, each person gets a unique username and a password. While usernames must be unique within your account, passwords can be duplicated. However, relying only on usernames and passwords is not considered very secure. Password policies and security. IAM allows you to set custom password policies, letting you decide how strong passwords must be. You can require a mix of uppercase, lowercase, numbers, and symbols. Still, common patterns like password 123x should be avoided for better security. Multi-factor authentication, or MFA. For stronger protection, IAM supports multi-factor authentication, or MFA. With MFA, users must enter a second code from a device, like a phone app, after their password. This extra step makes unauthorized access much harder. Setting up MFA. Setting up MFA is simple. You can use a virtual device, such as Google Authenticator, to scan a QR code and enter 2 consecutive codes. Once configured, your IAM user gains an extra layer of security. Introduction to programmatic access. Accessing Amazon Web Services, or AWS, does not always require logging into the management console. Many users and applications interact with AWS resources programmatically using tools like the AWS Command Line Interface, or CLI, APIs, PowerShell, or software development kits, known as SDKs. How AWS access keys work. For programmatic access, authentication is handled differently. Instead of a username and password, users or systems use access keys. These consist of an access key ID, which is 20 random uppercase alphanumeric characters, and a secret access key, which is 40 random characters. These keys are generated for AWS Identity and Access Management, or IAM, users. Configuring AWS CLI with access keys. To use the AWS CLI, you must configure it with your access keys. After installing the CLI, run the command AWS configure. Enter your access key ID, secret access key, default region, and preferred output format. This setup allows you to execute commands like creating or listing Amazon S3 buckets directly from your terminal. Best practices for access key management. Rotate your access keys regularly to enhance security. Always create a new key before deactivating the old one, test the new key, and then delete the inactive key. Never share or lose your secret access key.
When to use IAM roles. For applications running on Amazon EC2 instances, IAM roles offer a more secure and efficient way to grant access to AWS resources than using access keys directly. Introduction to IAM roles. IAM roles are a secure and efficient way to manage authentication and authorization in Amazon Web Services, or AWS. Instead of embedding credentials directly into your applications, IAM roles provide permissions through objects created within the Identity and Access Management, or IAM, system. How IAM roles work with EC2. When running applications on Amazon EC2 instances, you can associate an IAM role either during instance creation or after it is already running. Once linked, the EC2 instance can access AWS resources and make API calls, but only within the permissions defined by the role. This means there is no need to manually manage access key IDs. Instead, the role supplies dynamic, temporary access keys, ensuring secure and authorized access. Benefits and best practices. Using IAM roles for EC2 instances is considered a best practice. It eliminates the need for manual key rotation and reduces the risk of credential exposure. If you have multiple applications across several EC2 instances, roles make managing permissions and access much more efficient. Switching roles and permissions. Roles are not just for instances. Users can also assume roles, switching their permissions as needed. However, permissions do not combine, they are swapped entirely when switching roles. Introduction to EC2 authentication. When you launch a new Amazon Elastic Compute Cloud, or EC2 instance, authenticating securely is essential. The process varies slightly between Linux and Windows operating systems, but both rely on a fundamental concept, the use of key pairs. What is a key pair? A key pair consists of two cryptographic keys, a public key and a private key. These can be either ED25519 or 2048-bit Secure Shell version 2 or SSH2 RSA keys. However, ED25519 keys are not supported for Windows instances, EC2 Instance Connect, or the EC2 Serial Console. The key pair's main function is to encrypt and decrypt login information, ensuring secure access to your EC2 instances. Key pair usage for Linux and Windows. For Linux instances, the public key is stored by Amazon Web Services, or AWS, and you use your private key to connect via SSH. For Windows instances, the private key is used to decrypt the administrative password, which you then use to log in with Remote Desktop Protocol, or RDP. Remember, the private key is your responsibility. Managing your key pair. When creating an EC2 instance, you can download the key pair as a PEM file. Keep this file safe, as losing it means losing access. You can use the same key pair for multiple instances. Introduction to AWS Identity Federation. AWS Identity Federation lets users securely access AWS resources without needing a dedicated AWS Identity and Access Management, or IAM, user account. Instead, users can authenticate using existing accounts from external identity providers, known as IDPs, streamlining access and management. How identity providers work with AWS. Identity providers can include corporate directories like Microsoft Active Directory or public OpenID Connect web providers, such as Facebook, Google, and Amazon. This means organizations can grant access to AWS resources using users' existing credentials, eliminating the need to create separate IAM accounts for each user. Types of federation supported by AWS. AWS supports two main types of identity federation: Web Identity Federation and Security Assertion Markup Language, or SAML 2.0, based federation. Web Identity Federation enables authentication with public OpenID Connect providers, exchanging authentication tokens for temporary credentials linked to IAM roles. SAML 2.0 Federation allows Active Directory users to authenticate to AWS, supporting single sign-on and secure token exchange between the identity provider and AWS. Benefits and use cases. Most organizations use Microsoft Active Directory, making federated access an efficient way to manage permissions. This approach reduces administrative overhead and enhances security by leveraging existing identity systems. Additional resources. To learn more about AWS Federation and single sign-on, explore the dedicated courses on Amazon Cognito and identity management.
Introduction to Authorization and IAM. When working in your Amazon Web Services account, understanding authorization is key. Authentication verifies who you are, like entering a username and password. Authorization, on the other hand, determines what you can access after you are authenticated. This is managed by Identity and Access Management, or IAM. IAM users, groups, and roles. IAM users are individual accounts with credentials. Instead of assigning permissions to each user, best practice is to add users to IAM groups, which have policies attached. IAM roles are a bit different. They can be assigned to users or AWS services like EC2 instances, granting permissions without storing access keys. IAM policies and permissions. In AWS, permissions are granted through IAM policies written in JSON. You can use AWS managed policies for common tasks or create custom policies for specific needs. Policies can be attached to users, groups, or roles controlling access to resources. Creating and customizing policies. You can copy and modify existing AWS managed policies, use the AWS policy generator for guided experience, or build policies from scratch using the visual editor or JSON. Policy structure and best practices. Policies include statements with effects like allow or deny, actions, resources identified by Amazon resource names, and optional conditions. Always follow the principle of least privilege for security. Introduction to S3 authorization. Amazon Simple Storage Service, or S3, is a core storage solution within Amazon Web Services. Understanding how S3 authorizes access is crucial as it uses several mechanisms beyond standard identity and access management, or IAM policies. S3 bucket policies. S3 bucket policies are resource-based policies written in JSON format. Unlike IAM policies, which are identity-based, bucket policies attach directly to S3 buckets. They introduce the concept of principals, which can be IAM users, federated users, AWS accounts, or AWS services. Principals define who is allowed or denied access. Bucket policies can also include conditions, such as restricting access by IP address, providing fine-grained control over who can interact with your S3 resources. S3 Access Control Lists, or ACLs, offer another way to manage permissions. ACLs can be set at both bucket and object level, allowing different permissions for each. Permissions are granted to grantees, such as the bucket owner, everyone, authenticated users, or the S3 log delivery group. Unlike bucket policies, ACLs are less granular and do not support conditions or explicit denies. Permission precedence and conflict resolution. When multiple authorization methods overlap, AWS applies the principle of least privilege. By default, access is denied unless explicitly allowed. However, any explicit deny always overrides an allow. Summary. In summary, S3 authorization combines bucket policies and ACLs, each with unique features. Understanding their differences ensures secure and effective access management for your S3 resources.
What are NACLs? If you have worked with Amazon Web Services Virtual Private Clouds, or VPCs, you have likely encountered Network Access Control Lists, known as NACLs. NACLs operate at the network layer, providing a rule-based security feature that controls which network packets can enter or leave different parts of your VPC. How NACLs work. NACLs monitor and filter both inbound and outbound traffic at the protocol and subnet level. You can attach a NACL to one or more subnets within your VPC. If you do not create a custom NACL, your subnets are automatically associated with the default NACL, which allows all traffic in and out by default. NACL rule structure. Each NACL rule consists of 6 fields: rule number, type, protocol, port range, source, and allow or deny. Rules are read in ascending order, so careful sequencing is important. For example, leaving a gap of at least 50 between rule numbers makes it easier to add new rules later. You can specify common protocols like SHS or HTTP, or define custom ones. Key considerations. NACLs are stateless, meaning you must create separate rules for inbound and outbound traffic. They do not authorize user identities, but instead authorize network packets themselves to enter or leave a subnet. AWS security groups are essential for protecting your EC2 instances. They act like virtual firewalls, controlling which traffic can enter or leave your instance at the protocol and port level. While similar to Network Access Control Lists, or NACLs, security groups have some important differences that make them unique. Security groups use sets of inbound and outbound rules to filter traffic. Unlike NACLs, security groups do not have a deny action. If a packet is not explicitly allowed, it is simply dropped. Security groups are also stateful, meaning if you allow incoming traffic, the response is automatically permitted, so you do not need to create matching outbound rules. Each security group rule includes 8 fields: a name, a unique rule ID, IP version selection, type of protocol, protocol specification, port range, source definition, and an optional description. For example, you can allow SSH access from a specific IP address using TCP on port 22, while restricting all other ports. You might create a security group for SQL RDS instances and another for EC2 instances, permitting only SQL ports 1433 and 1434 between them. This approach enhances your AWS infrastructure security by limiting unnecessary access. Hi there, and welcome to Tech with Shaping Pixel. In this video, we are diving into Part 6 of the AWS Certified Advanced Networking Specialty ANS-C01 full crash course. AWS security groups are essential for protecting your EC2 instances. They act like virtual firewalls, controlling which traffic can enter or leave your instance at the protocol and port level. While similar to Network Access Control Lists, or NACLs, security groups have some important differences that make them unique. Security groups use sets of inbound and outbound rules to filter traffic. Unlike NACLs, security groups do not have a deny action. If a packet is not explicitly allowed, it is simply dropped. Security groups are also stateful, meaning if you allow incoming traffic, the response is automatically permitted, so you do not need to create matching outbound rules.
Each security group rule includes 8 fields: a name, a unique rule ID, IP version selection, type of protocol, protocol specification, port range, source definition, and an optional description. For example, you can allow SHS access from a specific IP address using TCP on port 22 while restricting all other ports. You might create a security group for SQL RDS instances and another for EC2 instances, permitting only SQL ports 1433 and 1434 between them. This approach enhances your AWS infrastructure security by limiting unnecessary access. The AWS Elastic Load Balancer, or ELB, is a managed service that distributes incoming requests across multiple targets, such as EC2 instances, Lambda functions, or containers, ensuring your applications remain available and resilient. Why use an ELB? Relying on a single instance can lead to downtime if it fails or struggles with traffic spikes. By introducing an ELB and multiple instances, you gain high availability and automatic traffic distribution, reducing the risk of outages and performance issues. Types of ELB. AWS offers 3 types of elastic load balancers. The application load balancer is ideal for HTTP and HTTPS traffic with advanced routing. The network load balancer handles ultra-high performance and low latency. The classic load balancer supports legacy EC2 classic environments. Key components. Every ELB uses listeners to define how requests are routed, target groups to organize resources, and rules to control traffic flow. Health checks monitor targets, ensuring only healthy resources receive traffic, while ELB nodes operate in selected availability zones for optimal distribution. Internal versus internet-facing ELBs. ELBs can be internal, serving only within your virtual private cloud, or internet-facing, accessible from the public internet. This flexibility supports both private and public application architectures. Let us explore how server certificates work with elastic load balancers, focusing on the application load balancer, or ALB, which supports both HTTP and HTTPS protocols for your web applications. HTTPS and server certificates. When you use HTTPS as a listener on your application load balancer, you enable encrypted communication between clients and your ALB. This requires a server certificate and a security policy. HTTPS is the encrypted version of HTTP, using protocols like Secure Sockets Layer, or SSL, and Transport Layer Security, or TLS. The ALB uses an X.509 certificate, which is a digital identity provided by a certificate authority. This certificate allows the ALB to terminate encrypted connections, decrypt requests, and forward them to resources in the target group. Certificate options for elastic load balancers. When configuring HTTPS listeners, you can select a certificate in 4 ways. Choose or upload a certificate to AWS Certificate Manager, or ACM, or choose or upload a certificate to Identity and Access Management, or IAM. ACM is preferred for its integration and ease of use. AWS Certificate Manager and IAM. ACM lets you create or import SSL or TLS certificates, simplifying deployment. IAM is used for third-party certificates or in regions where ACM is not available, offering flexibility for your elastic load balancer configurations. The Application Load Balancer, or ALB, is a key service in Amazon Web Services for distributing incoming application traffic. Operating at Layer 7 of the Open Systems Interconnection Model, or OSI model, the ALB is designed for advanced routing and visibility,
making it ideal for modern application architectures like microservices and containers. Target groups. Before setting up your ALB, it is best practice to configure target groups. A target group is simply a collection of resources, such as instances, IP addresses, or Lambda functions, that the ALB will route requests to. For example, you might create one target group for HTTP traffic on port 80 and another for secure HTTPS traffic on port 443. Creating an application load balancer. To create an ALB, navigate to the EC2 service in the AWS Management Console. After naming your load balancer and selecting listeners, such as HTTP on port 80, choose your availability zones and configure security settings. You can then associate your ALB with your previously created target group. Listener rules and monitoring. Listeners use rules to determine how traffic is routed. You can add conditions, like source IP addresses, to forward requests to specific target groups. Monitoring is handled by CloudWatch, providing metrics on healthy and unhealthy hosts, ensuring your application remains available and responsive. A network load balancer, or NLB, is designed to distribute incoming traffic across multiple targets, ensuring high availability and performance. Unlike the application load balancer, which operates at the application layer, the NLB works at layer 4 of the OSI model, focusing on TCP and UDP protocols. Key features includes support for listeners for TCP, Transport Layer Security, or TLS, and UDP, making it ideal for ultra-high-performance applications. It can process millions of requests per second and is the preferred choice if your application requires a static IP address. Cross-zone load balancing can be enabled or disabled, offering flexibility based on your needs. Configure an NLB in the Amazon Web Services Management Console by navigating to EC2 under Compute, then select Load Balancers. Choose to create a network load balancer, give it a name, and select internal or internet-facing. Set your listener protocol and port, such as UDP, on port 53 for DNS. Select your availability zones, configure security settings, and create or select a target group. Register your targets, review your settings, and create the load balancer. The process is straightforward and similar to configuring an application load balancer, but with different protocol and port options tailored for network-level traffic. The classic load balancer is one of the original load balancing options in Amazon Web Services, or AWS. It supports TCP, SSL or TLS, HTTP, and HTTPS protocols, but it is not as feature-rich as newer alternatives. Key features. Classic load balancers are unique because they support the EC2 Classic platform, which allowed instances to run in a single flat network shared with other customers. However, EC2 Classic is no longer available for accounts created after April 12, 2013. The Classic Load Balancer also supports TCP and SSL listeners, sticky sessions using application-generated cookies, and allows cross-zone load balancing to be enabled or disabled. Creation process. To create a Classic Load Balancer, navigate to the EC2 dashboard, select Load Balancers, and choose the Classic option. Name your load balancer, select your virtual private cloud or VPC, and configure listeners such as port 80. Choose your availability zones, assign security groups, and set up health checks to monitor instance health. Unlike other load balancers, you directly select EC2 instances instead of using target groups. Comparison and best practices. While the Classic Load Balancer is simple to set up, AWS recommends using the Application Load Balancer, or ALB, for most new deployments due to its broader feature set. EC2 autoscaling is a feature in Amazon Web Services, or AWS, that automatically adjusts your EC2 resources to match demand. By using custom metrics and thresholds, it helps ensure your infrastructure is always right-sized for your needs. How EC2 autoscaling works. Imagine you have a single EC2 instance running as a web server. As more users visit your site, the server's CPU utilization increases. With EC2 autoscaling, you can set a rule to automatically launch another instance when CPU usage reaches 75%. This distributes the load, preventing slowdowns. When demand drops and CPU utilization falls to 20%, autoscaling can terminate the extra instance, saving resources. Benefits of EC2 autoscaling. Automation is a key advantage. Your infrastructure can automatically add or remove resources, so your team does not have to manage this manually. This leads to greater customer satisfaction, as users experience fewer performance issues. Plus, you only pay for resources when they are running, optimizing costs. Real-world example. Pairing autoscaling with an elastic load balancer creates a flexible, scalable architecture. This combination ensures your applications remain responsive and cost-effective no matter how demand changes. EC2 autoscaling helps you automatically adjust your Amazon EC2 instances to meet demand. To get started, you need to define how new instances should be launched and configured. Launch configurations and templates. There are two main ways to define instance settings: launch configurations and launch templates. Both answer key questions, like which Amazon machine image or AMI to use, what instance type to select, whether to use spot instances for cost savings, and which security groups to apply. Launch templates are the newer, more advanced option, offering more features and a simpler, single-page setup. Creating a launch template. To create a launch template, you select your AMI, instance type, key pair, network settings, security groups, storage volumes, and add tags or user data for automation. Templates can be versioned for easy updates. Creating a launch configuration. Launch configurations are similar but have fewer advanced options. You still choose your AMI, instance type, security groups, and storage, but the process is more basic and less flexible than templates. Auto-scaling groups. Once your launch configuration or template is ready, you create an auto-scaling group. This group manages how many instances run, where they launch, and when to scale up or down based on policies. Elastic load balancers, or ELBs, and EC2 autoscaling are two powerful Amazon Web Services tools that work best when used together. Let us quickly explore how they complement each other to optimize both performance and cost. Why combine ELB and autoscaling? On their own, each service solves specific challenges. ELBs distribute incoming traffic across your resources using target groups and rules. EC2 autoscaling automatically adjusts the number of instances in response to demand. However, using only one can create extra manual work. Without autoscaling, you must manually add or remove instances from your ELB. Without an ELB, distributing traffic evenly to your autoscaling group becomes difficult. How they work together. When you attach an ELB to an autoscaling group, the ELB automatically detects new instances and distributes traffic to them. For application load balancers or network load balancers, you associate your autoscaling group with a target group. With classic load balancers, the EC2 fleet registers directly with the load balancer. This seamless integration ensures your infrastructure scales efficiently and traffic is always balanced. Quick how-to. To associate a load balancer, simply edit your auto-scaling group. Select your classic load balancer or choose the right target group for application or network load balancers. Then save your changes.
Combining ELBs and EC2 autoscaling streamlines operations, ensuring your applications remain responsive and cost-effective. Acme has already set up 2 EC2 instances in separate availability zones within a single virtual private cloud, or VPC, in the U East West 2 region. Each instance runs a copy of their website, and an application load balancer distributes traffic between them for high availability. Integrating ELB with Route 53. Now, Acme wants to integrate their load balancer with Route 53, Amazon's Scalable Domain Name System, or DNS, service. They have a public hosted zone in Route 53, which currently resolves their website's domain name to the public IP addresses of their EC2 instances. To improve efficiency, they will create an alias record. Alias records map friendly domain names directly to AWS resources like load balancers, making them more efficient than traditional CNAME records when everything is hosted within AWS. Securing with ACM. To secure their website with HTTPS, Acme uses Amazon Certificate Manager, or ACM, to obtain a free digital certificate. ACM is regional, so certificates must be requested in the same region as the load balancer. After validating domain ownership, the certificate can be attached to the load balancer by adding a secure HTTPS listener. Final steps and benefits. With this setup, HTTPS traffic is securely terminated at the load balancer, offloading encryption and decryption from the web servers. Removing the HTTP listener can enforce secure access, ensuring both high availability and robust security for Acme's website. Acme, a global company, faced slow website performance for customers in the United States. Instead of deploying more web servers, they chose to enhance speed and security by integrating their Elastic Load Balancer, or ELB, with Amazon CloudFront and AWS Web Application Firewall, or WAF. CloudFront integration. Amazon CloudFront is a content delivery network that caches content at AWS edge locations closer to users, reducing latency and improving performance. Acme created a CloudFront distribution with their ELB as the origin. By selecting the North America and Europe price class, they kept costs down while targeting the regions with the most complaints about speed. Domain and routing setup. To use their own domain, Acme added an alternate domain name, such as www.acme.com, to the CloudFront distribution. They attached a digital certificate for secure HTTPS traffic and updated the alias record in Amazon Route 53 to route users to CloudFront instead of directly to the ELB. AWS WAF security. For security, Acme implemented AWS Web Application Firewall, or WAF. They created an WAF Access Control List, or ACL, with rules to monitor and control HTTP and HTTPS requests, protecting their content from common web exploits. By integrating ELB with CloudFront and AWS WAF, Acme improved website speed for U.S. customers and strengthened security, all without deploying additional servers. Acme is expanding its website deployment from the United States to Europe with plans for North America. Their goals? Ensure users always reach the fastest, healthiest endpoint, adapt to infrastructure changes, and avoid constant updates to Route 53, Amazon's DNS service. How Global Accelerator works? By integrating Elastic Load Balancer, or ELB, with Amazon Global Accelerator, Acme can meet these goals. Global Accelerator provides a fixed set of IP addresses for accessing endpoints across multiple regions. This means Acme can reorganize services or add regions without updating Route 53 every time. Integration steps. To integrate, Acme creates an accelerator in Global Accelerator. They name the accelerator, set up one or more listeners for specific ports and protocols, and defined endpoint groups for each region.
Each group includes health checks and endpoints, which can be application load balancers, network load balancers, EC2 instances, or elastic IP addresses. Once deployed, the accelerator receives a DNS name which Acme maps to their website's friendly name using Route 53. Key benefits. Global Accelerator uses AWS edge locations for faster performance, checks endpoint health, and always routes users to the optimal, healthy endpoint. It supports both TCP and UDP traffic, making it a robust solution for global applications. Acme has been using Elastic Load Balancers, or ELBs, with Amazon Web Services to provide access to its website hosted on EC2 instances. Now, as Acme plans to containerize its application, the focus shifts to Amazon Elastic Kubernetes Service, or EKS. Why integrate ELB with EKS? When moving to EKS, Acme still needs to efficiently distribute traffic to the containers running its website application. Integrating an ELB with EKS ensures that incoming requests are balanced across all available containers, maintaining performance and reliability as the application scales. Recommended load balancer types. Historically, deploying a service on EKS with a YAML file would create a classic load balancer. However, it is now recommended to use either an application load balancer or a network load balancer with EKS. Classic load balancers are still supported, but newer options offer better features and flexibility. Integration methods. To integrate ELB with EKS, you can either create an ingress controller which sets up an application load balancer, or define a load balancer type in your service YAML file to deploy a network load balancer. Both methods are supported and widely used. Final steps and benefits. Once configured, your load balancer appears in the Amazon Web Services console. You can then integrate it with other AWS services, such as using Route 53 to map a friendly domain name to your load balancer using an alias record. AWS is known for listening to its customers, and the AWS Gateway Load Balancer is a perfect example of customer-driven innovation. This service was designed to address real challenges faced by organizations using virtual appliances in the cloud. Customer challenges. Many AWS customers rely on virtual appliances from AWS partners and the AWS Marketplace. However, deploying and scaling these appliances was often complex. Directing all inbound and outbound traffic from an internet gateway or virtual private gateway to a specific Elastic Compute Cloud or EC2 instance in a virtual private cloud or VPC was a major hurdle. AWS Gateway Load Balancer simplifies this process. By using virtual private cloud ingress routing, customers can forward all traffic to the Gateway Load Balancer by updating route tables. This allows seamless redirection of traffic to virtual network appliances for security processing without disrupting normal request and response flows. The service uses a single point of access for all traffic, scales appliances with demand, and automatically routes traffic only through healthy appliances. Key benefits. With Gateway Load Balancer, you can transparently inspect and act on network packets, ensuring sticky, symmetric, and transparent flows. It brings flexibility and reliability to your cloud networking. Closing. AWS Gateway Load Balancer, customer-driven innovation making cloud networking simpler and more powerful. The Gateway Load Balancer is a powerful tool designed to protect and manage network traffic in your cloud environment. It is made up of two main components that work together to deliver security and performance. How the Gateway Load Balancer works. First, there is the VPC Gateway Load Balancer endpoint.
This is set up in the Virtual Private Cloud, or VPC, where you want to secure your traffic. The second part is the actual gateway load balancer, which directs network traffic to a group of Amazon EC2 instances. These instances run third-party network appliance software, providing advanced security features. Geneve Tunneling Protocol explained. To make all of this possible, the gateway load balancer uses a tunneling protocol called Geneve, which stands for Generic Network Virtualization Encapsulation. Geneve creates a logical Layer 2 network by encapsulating data in User Datagram Protocol, or UDP, packets. This approach allows for flexibility and leverages the performance benefits of modern network interface cards. Geneve operates on port 6081, while health checks use HTTP port 80. Traffic flow and security. A tunnel is established between the gateway load balancer and the EC2 instances. Traffic is encapsulated, sent through the tunnel, and examined by security appliances before reaching its destination, ensuring both separation and security.
Gateway load balancer architecture is essential for integrating advanced traffic inspection and security into your Amazon Web Services, or AWS, environment. Let us break down how this architecture works and why it is so effective. Key components. At the heart of this setup is the Gateway Load Balancer endpoint, often called GWLBE. Each endpoint is typically placed in its own subnet within every availability zone. These endpoints can be added to route tables as the next hop, seamlessly integrating the gateway load balancer into your virtual private cloud, or VPC, traffic flow. GWLBE is similar to AWS Private Link, enabling centralized control across multiple accounts and VPCs. Setup steps. To set up a gateway load balancer, first, locate your partner's virtual appliance software, often found in AWS Marketplace. Next, launch the appliance instances in a dedicated security VPC. Then, create a gateway load balancer and a target group with those instances. After that, establish gateway load balancer endpoints in the VPC where traffic inspection is needed. Finally, update route tables so that the Internet Gateway directs traffic through these endpoints. Traffic flow. This architecture ensures that both application and Internet traffic are routed through the gateway load balancer endpoints, enabling robust centralized security and inspection for your AWS workloads. Let us break down the gateway load balancer architecture, a powerful way to secure and scale your applications in the cloud. This setup uses both application load balancers and gateway load balancers, each serving a unique purpose within your Amazon Virtual Private Cloud, or VPC. Packet flow overview. When a customer accesses your web application, their request first lands at the application load balancer in a public subnet. However, the Internet Gateway is configured to route this incoming traffic to a gateway load balancer endpoint. This endpoint forwards the traffic to the gateway load balancer, which sits in a dedicated security VPC. Here, packets are encapsulated using the Geneve tunneling protocol and sent to a security appliance for inspection. Security appliance processing. The security appliance analyzes the packets based on its configuration. After inspection, the packets return to the gateway load balancer, where encapsulation is removed. The traffic is then sent back to the gateway load balancer endpoint and finally directed to the application load balancer, which targets your application in the private subnet. Return path and scaling benefits. The response from your application follows a similar path in reverse, ensuring all traffic is inspected.
This architecture allows you to horizontally scale your security appliances, adapting to application load and leveraging third-party solutions from the AWS marketplace for robust, flexible protection. Digital certificates are a crucial part of our daily online experience. Every time you visit a website using HTTPS, you are relying on digital certificates to keep your connection secure and trustworthy. How digital certificates work. Digital certificates validate the identity of websites, services, or users. They contain a public key which allows us to set up secure communications, verify digital signatures, and ensure data integrity. Trust in these certificates is essential for secure connections. Public versus private certificate authorities. To obtain trusted digital certificates, we turn to certificate authorities, or CAs. Public CAs are widely trusted by operating systems and browsers, issuing certificates for public-facing services. Private CAs are managed internally, used for internal applications, and require manual trust configuration. Challenges of managing certificates. Managing digital certificates can be complex. Tasks include handling certificate requests, renewals, revocations, and maintaining secure CA infrastructure. Certificate revocation lists, or CRLs, help track certificates that should no longer be trusted. AWS Certificate Manager features. AWS Certificate Manager simplifies certificate management. It provides free SSL and TLS certificates from trusted public CAs for AWS services, automates renewals, and manages private CAs, reducing manual effort and minimizing the risk of expired certificates disrupting your services. AWS Certificate Manager is a regional service that lets you request public certificates to secure your AWS resources. Remember, you must use the correct region for your service, like Ireland for an application load balancer, or North Virginia for CloudFront. Requesting a certificate. To begin, open AWS Certificate Manager in your chosen region and select Request a Certificate. You will be prompted to choose between a public or private certificate. If you have not set up a private certificate authority, only the public certificate option will be available. Validation methods. Next, enter the fully qualified domain names you want to secure, such as www.acme.com. Then choose a validation method, DNS validation or email validation. DNS validation requires adding a scene name record, while email validation sends messages to the domain's registered contacts. DNS validation details. If your domain uses Route 53 and you have the right permissions, AWS can add the scene name records automatically. Otherwise, you must add them manually. Once the DNS records are in place, AWS will validate your ownership and issue the certificate. Using the certificate. Now return to your application load balancer. Add a new listener for HTTPS. Select your newly issued certificate and configure the forwarding rules to your target group. Finally, you can remove the HTTP listener to enforce HTTPS, ensuring your application is securely protected. AWS Certificate Manager makes it easy to manage digital certificates for your applications. With no extra setup, it can issue public certificates, streamlining the process of securing your websites and services. How AWS Certificate Manager works. If you need private certificates, AWS Certificate Manager requires you to create a Private Certificate Authority, or CA. This is a managed service, meaning AWS handles the infrastructure, high availability, and backups for you. To get started, you set up a certificate hierarchy beginning with a root certificate authority. The root CA creates a self-signed certificate which can be imported into devices to establish trust.
Understanding private certificate authorities. Root certificate authorities do not issue certificates directly to devices or services. Instead, subordinate certificate authorities, which are signed by the root CA, handle this task. When a subordinate CA issues a certificate, its signature can be verified through the chain of trust, ensuring secure connections. Why use private certificate authorities? Private CAs are essential for internal applications, especially when you need SSL or TLS certificates for internal domains that public CAs cannot validate. AWS simplifies this process by managing the CA for you. Pricing and management. AWS Certificate Manager Private Certificate Authority is a paid service with monthly fees for each CA and one-time fees for each private certificate issued. AWS Network Management. Welcome to your guide for mastering network management in Amazon Web Services, or AWS. This course is designed to help you prepare for the AWS Certified Advanced Networking Specialty Certification, focusing on the latest updates and essential networking concepts. This course is ideal for anyone aiming to deepen their understanding of AWS networking services in preparation for the exam. We will provide a high-level introduction to the core network management tools and services available in AWS. Whether you are experienced in designing, implementing, or operating complex AWS and hybrid networking architectures, this course will reinforce your knowledge and help you build confidence for the exam. Key AWS networking tools. Throughout the course, you will explore AWS Config, AWS Trail, Amazon Inspector, and VPC Flow logs. Each tool will be explained from the ground up, ensuring you understand their roles in managing and securing cloud networks. We will also discuss strategies for solving common challenges in cloud networking and maintaining network security at scale. Exam preparation and next steps. By combining this course with preparation Q&A video available in our YouTube channel at Tech with Shaping Pixel, you will cover all the key topics from the AWS Certified Advanced Networking Specialty Exam Guide, ensuring you are fully prepared to sit for the certification. Managing a handful of machines is straightforward, but as your infrastructure grows into the dozens or hundreds, maintaining consistency becomes a real challenge. Automation is key to reducing human error and ensuring every machine is configured the same way. Why AWS Config matters. AWS Config is designed to help you automatically discover and track your AWS resources. It provides a complete inventory, including configuration details and a history of changes, so you always know how your resources are set up at any point in time. Enabling AWS Config. By default, AWS Config is disabled when you create a new account. To get started, you need to enable the AWS Config Recorder. This module tracks changes in your resource configurations and records them as configuration items for future reference. The AWS Config Recorder. The AWS Config Recorder operates within a specific region and can monitor all current and future resources or adjust selected types. It even supports global resources like AWS Identity and Access Management users, groups, and roles, giving you comprehensive visibility. Delivery and retention. AWS Config typically delivers its findings to an Amazon Simple Storage bucket. You can also send detailed configuration change notifications to Amazon Simple Notification Service or Amazon Event Bridge. By default, AWS Config retains data for 7 years, but you can customize this period. AWS CloudTrail is a service designed to record and track events in your AWS account. It captures both application programming interface, or API requests, and non-API actions, providing visibility into user and service activity across your environment. Types of events. CloudTrail categorizes events into 3 types: management events, which track control plane operations like creating users or databases; data events, which log resource-level actions, such as Amazon S3 Object Access; and insight events, which highlight unusual activity to help identify potential issues. Trails and their scope. You can configure CloudTrail with different types of trails. An all-region trail records events across every AWS region in your account and is the recommended option for comprehensive visibility. Single-region trails focus on one region, while organization trails capture events from all accounts within an AWS organization. CloudTrail Lake lets you store, review, and query events for up to 7 years using event data stores. You can filter and analyze events, including those from AWS Config and external sources. Integration with partners like CrowdStrike and GitHub is possible through CloudTrail channels. Accessing and using CloudTrail. By default, CloudTrail is enabled for new AWS accounts. You can view the last 90 days of activity in the Event History dashboard, filter events, and download logs for further analysis or compliance needs. AWS CloudTrail is a powerful tool that records activity across your Amazon Web Services environment, whether you use a single region, all regions, or an entire AWS organization. But what does this mean for your business? Security and visibility benefits. CloudTrail acts as a security ally, capturing detailed records of every API call. If there is an unsuccessful sign-in attempt or someone tries to run a restricted API, your security team can quickly identify what happened, who was responsible, and take steps to prevent it from happening again. This enhanced visibility helps you spot weaknesses in your infrastructure, giving your engineers the information they need to reinforce security boundaries and follow operational best practices. Consolidated analysis and insights. With CloudTrail Trails and CloudTrail Lake, you can consolidate activity from multiple regions into a single Amazon Simple Storage Service bucket. This single pane of glass approach simplifies analysis, making it easier to identify patterns and audit activity at scale. CloudTrail Insights, when enabled, automatically detects and highlights unusual behavior, providing early warnings for potential threats. Auditing and compliance. CloudTrail logs capture essential details like who performed an action, when, from where, and what was changed. This comprehensive audit trail helps your business maintain governance, meet regulatory requirements, and ensure accountability across your AWS resources. Amazon Inspector is a managed security service from Amazon Web Services, or AWS, designed to help you identify vulnerabilities in your EC2 instances and the applications running on them, no matter the stage of development or deployment. How Amazon Inspector works. The service uses automated assessments based on hundreds of best practices and known security weaknesses. It checks for common vulnerabilities and exposures, or CVEs, which are well-documented security threats. Amazon Inspector also leverages Center for Internet Security benchmarks, global standards for protecting data and IT resources. By analyzing runtime behavior and security best practices, it provides a comprehensive security overview. Key features and customization. Amazon Inspector is agent-based, requiring software agents on your EC2 instances. This makes it easy to integrate with your existing AWS infrastructure. You can customize assessments by selecting packages that fit your organization's standards, ensuring specific security loopholes are identified and addressed quickly. Compliance and reporting. After each assessment, Amazon Inspector generates detailed reports highlighting findings and threats. These records are valuable for auditors and help maintain compliance with certifications like PCI. Benefits and scalability. Amazon Inspector is cost-effective compared to traditional solutions, scales with your organization, and automates security assessments, reducing the need for specialized security expertise. Amazon Inspector is a managed security service from Amazon Web Services, or AWS, designed to help you identify vulnerabilities in your EC2 instances and the applications running on them, no matter the stage of development or deployment. How Amazon Inspector works. The service uses automated assessments based on hundreds of best practices and known security weaknesses. It checks for common vulnerabilities and exposures, or CVEs, which are well-documented security threats. Amazon Inspector also leverages Center for Internet Security benchmarks, global standards for protecting data and IT resources. By analyzing runtime behavior and security best practices, it provides a comprehensive security overview. Key features and customization. Amazon Inspector is agent-based, requiring software agents on your EC2 instances. This makes it easy to integrate with your existing AWS infrastructure. You can customize assessments by selecting packages that fit your organization's standards, ensuring specific security loopholes are identified and addressed quickly. Compliance and reporting. After each assessment, Amazon Inspector generates detailed reports highlighting findings and threats. These records are valuable for auditors and help maintain compliance with certifications like PCI. Benefits and scalability. Amazon Inspector is cost-effective compared to traditional solutions, scales with your organization, and automates security assessments, reducing the need for specialized security expertise. To configure Amazon Inspector, start with your Amazon Elastic Compute Cloud, or EC2, instances. In this example, there is one Linux and one Windows instance, both tagged with an operating system key and the appropriate value. Agents are already installed on each instance. When reviewing your assessment runs, understanding findings is key. Each run generates findings that highlight issues or areas for improvement, categorized by severity and detailed for easy analysis. Navigating severity levels. In the console, findings are grouped by severity: high, medium, low, and informational. For example, one assessment run revealed 4 findings for Linux and 230 for Windows, with most high-severity issues on Windows. Exploring high-severity findings. High-severity findings provide detailed information, including the unique resource name, run name, target, template, and assessment times. You can see which rules package triggered the finding, such as the Center for Internet Security benchmarks, and get direct links to affected instances. Medium and low-severity examples. Medium findings might flag issues like allowing root logins over secure shell, or SSH, on Linux, increasing brute force risk. Low-severity findings often involve insecure protocols with recommendations to switch to encrypted versions for better security. Informational findings and exporting data. Informational findings may note unused open ports, suggesting you disable unnecessary services. You can export all findings as a comma-separated values file for easier tracking and team collaboration. Prioritize high-severity findings first, then address medium and low issues. Use filters and exports to streamline your remediation process and keep your environment secure. Amazon Inspector is a powerful tool for assessing the security of your AWS resources, but its true strength comes from how it integrates with other AWS services, specifically Amazon CloudWatch, and AWS CloudTrail. These integrations enhance your ability to monitor, track, and audit your security assessments. Monitoring with Amazon CloudWatch. With Amazon CloudWatch, you can keep a close eye on Amazon Inspector's activity. CloudWatch allows you to monitor specific metrics for both assessment targets and assessment templates. For example, you can track the number of assessment runs within your account using an aggregate metric. These insights help you understand the performance and activity of Amazon Inspector, giving you detailed statistics to inform your security decisions. Auditing with AWS CloudTrail. From an auditing perspective, AWS CloudTrail plays a crucial role. Every API call made by Amazon Inspector is logged by CloudTrail. This means you can see exactly who performed what action and when. All of this information is stored in CloudTrail log files within Amazon Simple Storage Service, or S3, making it easy to review and audit your security operations. Benefits of integration. By combining Amazon Inspector with CloudWatch and CloudTrail, you gain enhanced monitoring and auditing capabilities. This integration supports better governance and security audits, ensuring your environment remains secure and compliant. Amazon Inspector is a powerful tool for enhancing your cloud security, but it does come with some important limitations. When setting up assessments, you can include up to 500 agents per assessment, and this number cannot be increased. Each account has a default limit of 50,000 assessment runs, but if you need more, you can request an increase from Amazon Web Services customer support. Additionally, you are limited to 500 assessment templates and 50 assessment targets by default, both of which can be increased if necessary. It is also important to note that rule packages may have limitations depending on the operating system you are using. Cost structure. Now, let us talk about costs. Amazon Inspector uses a straightforward pricing model, UK per agent per assessment run, calculated monthly. For example, running one agent across 20 assessments counts as 20 agent assessments. Similarly, 2 agents across 5 assessments would be 10 agent assessments. The starting price is 30 cents per agent assessment per month, and discounts are available as your usage increases. There are no upfront fees or ongoing maintenance costs, making it a cost-effective choice for many organizations. To sum up, Amazon Inspector offers robust security insights with clear service limits and a simple, scalable pricing structure. Always review your needs and contact Amazon Web Services customer support if you require higher limits. VPC flow logs let you capture IP traffic information flowing between network interfaces in your virtual private cloud, or VPC. With hundreds of resources communicating across subnets and VPCs, these logs are essential for troubleshooting network issues and enhancing security. Key features and limitations. Unlike S3 or CloudFront access logs, VPC flow logs send data to CloudWatch logs, not Amazon S3. However, there are some limitations. You can only view flow logs for peered VPCs within the same account, and EC2 Classic resources are not supported. Once created, a flow log cannot be changed. You must delete and recreate it to modify settings. Setting up VPC flow logs. You can create flow logs for a network interface, a subnet, or the entire VPC. During setup, select a filter for accepted, rejected, or all traffic. Assign an IAM role with permissions to deliver logs to CloudWatch. Each network interface uses a separate log stream, and logs are captured every 10 to 15 minutes. Understanding log entries. Each log entry includes details like version, account ID, interface ID, source and destination addresses, ports, protocol, packet and byte counts, timestamps, action, and log status. The action field is crucial for identifying accepted or rejected traffic. Practical use case. If network traffic is blocked, VPC flow logs help pinpoint whether security groups or network access control lists are the cause.
Thanks for watching. If you haven't subscribed to our YouTube channel yet, we'd love for you to join our growing community. Just hit that subscribe button. Want a downloadable PDF of these questions and answers? You can grab it from our website, www.shapingpixel.com. Full link is in the description below. Happy learning!